Hello there and welcome to Science for Sleep, the quiet little corner where curiosity can stretch out its arms, loosen its shoulders, and slowly settle in. Tonight we're going to drift into one of the strangest questions humans have ever asked. It's a question that sounds like a riddle but is also at the heart of how we imagine reality itself. Could the universe be finite and infinite at the same time? That sounds impossible, doesn't it? Like saying your mug of tea is both full and empty, or that a path both ends and never ends. But with the universe, the more we look, the stranger the answers become, and the stranger the questions get as well. Before we take that journey together, I'd love to know something small but grounding. Where are you listening from tonight? Are you in a quiet bedroom, tucked under a blanket, maybe with the soft light of a lamp still glowing? Or are you listening from a busy place, trying to carve out a moment of calm in the middle of everything else? And while you're thinking about that, let me add one more question, a little fitting for tonight's theme. When you look up at the night sky, do you feel like you're staring at something endless? Or do you feel like there must be some edge out there, some border to all that darkness? It's a very personal thing, how each of us senses the night above. If you find yourself enjoying this kind of gentle exploration, if you like the way these big questions can be softened into something almost like a bedtime story, it would mean a lot if you gave this video a like and maybe even subscribed. It helps this little space find others who might be searching for a calm way to wander too. And who knows, maybe the more of us there are, the more connected this odd shared search for answers will feel. Now, let's begin. Not quickly. Not with the rush of a lecture or the weight of a textbook, but slowly, almost like watching steam curl from a cup of tea. Because when we ask whether the universe could be finite and infinite at once, we're not only tugging at scientific theories, we're also tugging at something human, our sense of what it means for something to end, or to have no end at all, our sense of safety in limits, and our unease in boundlessness. So let's settle into it. When you think of the word finite, you probably imagine something contained. A box with edges, a road that eventually stops, a lifetime measured in years. Finite means we can measure it, count it, say when it began, and know when it ends. Infinite feels like the exact opposite. No edges, no counting, no finishing point. And yet in the strange ways scientists have come to understand the cosmos, there are models where both things might be true at once. It's not simply a matter of picking one or the other, like choosing between two flavours of ice cream. Instead, it might depend on how you ask the question, what scale you look at, and how you define your words. This isn't just a curiosity for scientists. Humans have wrestled with it since long before telescopes or equations. Thousands of years ago, ancient storytellers imagined what lay beyond the visible world. For some, the earth floated on an endless sea. For others, the sky was a dome held up by pillars. These weren't silly guesses. They were serious attempts to explain something that felt larger than comprehension. To look out and see something that had no visible end was unsettling, so stories built edges. Edges made things manageable. The finite brought comfort. But then there were always whispers of the infinite. Philosophers, even in the earliest civilizations, argued that if the world had a boundary, then what was beyond it? And if there was something beyond, didn't that mean the world wasn't bounded after all? This circular puzzle has never really gone away. It shows up in religion, in mathematics, in science, and in our own late-night thoughts when the stars seem too many to count. And that is why tonight, we're going to let ourselves drift into the puzzle. Could the universe really be both finite and infinite at the same time? As we wander, we'll look at how humans have imagined limits, how science has defined space, how mathematics handles infinity, and what modern physics says about the edges of everything. Along the way, we'll notice that this isn't just a technical question. It's also deeply emotional. To believe in a finite universe is to believe in borders. To believe in an infinite one is to accept a kind of endless openness. Both feelings shape the way we live, and maybe even the way we sleep. And so, as you relax into this exploration, Imagine yourself floating at the edge of what you know. Behind you, everything familiar. Ahead of you, something that may or may not end. That's where we'll begin. When we think about infinity in the abstract, it can feel distant, like a mathematical trick or a puzzle written on paper. But when we connect it to the world we actually live in, it starts to become much more tangible. For most of human history, infinity wasn't a concept from textbooks. It was the experience of looking upward, the endless stretch of the night sky, the horizon that never seemed to arrive, the sense that if you kept walking or kept sailing, there might always be more. Boundaries and infinity have always been tied to our most basic senses. To wonder whether something ends or goes on forever is to wonder about the very shape of our world. Think about the way the horizon looks when you're standing on a beach. The water reaches out in every direction until it meets the sky. Your eyes tell you there's an edge out there, a place where sea and sky touch. But your mind knows that isn't really the end. If you could sail toward it, the horizon would retreat. The edge you thought you saw was never there at all. In that moment, you're caught between two realities. Your senses insist there's a limit. Your reasoning tells you it's endless. This tension between what feels finite and what might be infinite is one of the oldest experiences humans have had. Our ancestors looked at the sky and faced the same puzzle. On a clear night, stars spread across the dark like scattered grains of salt, so many that no one could count them all. To look up was to be reminded of smallness, and smallness made boundaries tempting. The sky had to end somewhere, perhaps at a dome, perhaps at the home of the gods, perhaps at a realm unreachable by mortals. Boundaries provided comfort. They made existence feel manageable. After all, if the world truly had no end, then what did that say about us, the tiny beings living inside it? The human brain likes edges. It likes to sort things into categories, into beginnings and endings. Children ask when something starts and when it stops. Adults carve calendars into days, months and years. Even the rhythm of sleep and waking is a boundary, separating one kind of consciousness from another. Boundaries give structure. Without them, life feels shapeless. But the natural world constantly undermines this neat preference. The ocean rolls on without any visible wall. The desert stretches past the horizon. The sky, most of all, never closes. Standing under the night, the human sense of order is confronted by something that seems to refuse all boundaries. It is not surprising, then, that cultures across history built myths that framed the sky as a kind of roof. The ancient Mesopotamians imagined a great dome overhead, made of solid material, keeping the waters of heaven from falling down on the earth. In Egypt, the goddess Nut stretched her body across the world as the arching sky. In Norse stories, the skull of a giant was placed overhead to form the heavens. These were not naive guesses, but practical ways of reconciling experience with psychology. People needed a boundary, and so they gave the sky one. At the same time, infinity was always lurking. Even within these myths, questions arose. If there is a dome, what lies beyond it? If the earth floats on water, what lies beneath? If the world was created, what surrounds the place it was set into? Each answer only pushed the boundary farther out, like chasing the horizon on the sea. The sense of endlessness refused to disappear. This duality shows up in everyday human behaviour. We build fences, walls and borders because we like to know where things stop. Yet we also dream of exploration, of crossing the sea, of seeing what lies on the other side. The same brain that seeks comfort in edges also hungers for the possibility of no edges at all. The night sky remains the clearest symbol of this. It is at once bounded in our sight and boundless in imagination. Even in modern times, with telescopes mapping galaxies, the sense of endlessness remains just as powerful. We can measure distances in light years. We can draw diagrams of the observable universe. But none of this changes the feeling of stepping outside on a quiet night and seeing more stars than thoughts. The mind knows they are not infinite in number. The heart insists they might as well be. Boundaries are deeply personal as well. Each of us has experienced the comfort of something finite, a finished book, a clear conclusion, a journey with a start and an end. At the same time, we've all brushed against the unease of the infinite, the long night that feels endless, the waiting that stretches without conclusion, the overwhelming thought of eternity when lying awake. Our sense of infinity isn't only about the cosmos, it is tied to the way we live minutes and hours. The connection between endless skies and human psychology is worth pausing on. Children often imagine the sky as a ceiling. Only later, when they learn about space, do they encounter the idea that the sky doesn't stop. For many, that first realization is dizzying. The idea that the sky is not a dome but an opening into something without clear limits can be both thrilling and unsettling. The sense of security provided by an edge gives way to a sense of awe and sometimes fear. This oscillation between wanting an edge and confronting endlessness has shaped philosophy as much as myth. Ancient Greek thinkers debated whether the cosmos was finite or infinite. Aristotle leaned toward the finite. He imagined the heavens as a set of nested spheres, ending at the outermost sphere of fixed stars. Infinity was something he considered incomplete, imperfect. For him, a finite cosmos was more elegant. But other philosophers, like the atomists, were more comfortable with the infinite. They suggested space stretched without end, filled with countless worlds beyond our own. Their idea was unsettling to many, but it resonated with the endless skies that anyone could see. Over centuries, this back and forth continued. Religious traditions often favoured finite worlds with defined boundaries, sometimes with heavens beyond. Scientific inquiry, especially as telescopes improved, pushed the boundaries outward again and again. What was once a sky of stars became a galaxy. What was once a galaxy became a universe filled with galaxies. Each step eroded the comfort of boundaries and forced us closer to the infinite. Yet even now, the human brain does not easily accept infinity. Try counting without end. Try imagining a universe with no border at all. At some point, the mind strains against it. We're not naturally built to picture infinity. Instead, we approach it through metaphors. We compare it to horizons, to unending seas, to endless numbers. None of these metaphors capture it completely, but they give us something to hold on to. The endless skies above are perhaps the oldest and most natural metaphor of all. And so, the sense of boundaries and infinity remains entwined. On one hand, we need edges to structure our lives. On the other, the universe resists those edges at every turn. To live as a human being is to live in this tension. We prefer the finite. We are surrounded by the infinite. It is interesting to note how differently people react to this tension. For some, the thought of an infinite universe is comforting. It means there will always be more to discover, that existence cannot be contained, that no final wall will ever hem us in. For others, infinity is a source of anxiety. To think of something with no end can feel overwhelming, like falling without ever reaching the ground. Both reactions are deeply human, and both find their origin in the same simple act, looking up at the endless sky. When astronomers today describe the universe, they still wrestle with this duality. The observable universe is finite. We can map it, measure it, calculate its size. But beyond what we can see, we don't know whether space stops or continues. For all our science, we're still in the same position as our ancestors on the beach, staring at a horizon that retreats whenever we approach. The human sense of boundaries and endless skies is, in many ways, the foundation of the larger question we're asking tonight. Could the universe be finite and infinite at once? The answer might lie in the fact that our senses and our reasoning pull in different directions. The eyes tell us there is an edge. The mind whispers that there isn't. Between those two, we live with the paradox. When we try to imagine infinity today, we reach for mathematics, telescopes, and cosmology. But for most of human history, infinity was not a number or an equation. It was a story. To make sense of the sky and the land, to answer the question of where the world ended, ancient people turned to myth. They gave shape to the unknown, borders to the endless, and meaning to the terrifying possibility that there might be no edge at all. The idea of the world having an edge was as natural as breathing to our ancestors. After all, when you walk across a plain, eventually you reach a mountain or a river. When you travel down a river, you eventually find the sea. Everything in daily life appeared bounded. Crops had edges, homes had walls, villages had borders. Why wouldn't the world itself be the same? It seemed sensible to imagine the earth as a flat surface surrounded by some barrier, something holding everything in. But then came the unsettling question. If there is an edge, what happens if you go beyond it? The answers varied widely, and each culture filled the void with its own imagination. For the ancient Mesopotamians, one of the oldest civilizations on Earth, the world was a flat disk floating on an endless sea. Above was a solid dome, the firmament, separating the waters of the heavens from the waters below. The stars were holes in that dome, little points where divine light shone through. Beyond the dome lay more waters, endless and mysterious. For them, the edge of the world was not so much a cliff you could fall from, but a limit enforced by gods. To cross it would be to leave the realm of mortals entirely. In ancient Egypt, the vision was different but just as finite. The sky was personified as the goddess Nut. Her body arched across the earth. Beneath her lay Geb, the god of the land. Every night Nut swallowed the sun, and every morning she gave birth to it again. The sky was not endless in this vision. It was a body, a ceiling, a boundary stretched overhead. To look at it was to look at the divine. Yet still the question remained. If Nut's body curved across the world, what lay beyond her? Myth rarely erased the puzzle of infinity. It simply gave it a more human face. In the myths of the Norse, the world was constructed from the body of a slain giant, Ymir. His flesh became the earth, his bones the mountains, his blood the seas, and his skull the sky. Again, we see the idea of a ceiling, something finite overhead. The cosmos itself was crafted from a body, which meant it had limits and structure. And yet surrounding this world was Ginnungagap, the great yawning void, an emptiness with no end. Here we find the same paradox that continues to trouble us today. The human realm was finite, bordered and measurable, but beyond it lay something boundless, something the myths admitted was infinite, though terrifyingly so. Other cultures imagined the world as resting on the back of a giant animal. In India, the earth was sometimes pictured as being supported by elephants standing on the back of a vast turtle. In parts of China, a giant turtle carried the land. In the Americas, myths told of a cosmic serpent holding the world in place. These images made the universe stable, finite, and safe. If the earth rested on something, then it had an anchor. But inevitably, a curious child or philosopher would ask, and what does the turtle stand on? The answer was often evasive. It's turtles all the way down. A phrase that captures, even in humour, the infinite regress hidden in the heart of every myth. For the Greeks, the question of boundaries took on a new flavour. Early Greek thought imagined Oceanus, a great river encircling the world. This was not simply a metaphor. It was a way of explaining why ships that sailed too far might not return. The edge of the world was a watery boundary, a limit that could not be crossed. Yet Greek philosophers were among the first to openly entertain the possibility of infinity. Some believed the cosmos had no edge at all, extending forever in every direction. Others argued this was impossible, that infinity was messy and imperfect, and that the universe had to be a contained sphere. This debate set the stage for centuries of arguments between the finite and the infinite. In Polynesian traditions, the cosmos was layered. The sky had multiple levels, stacked above one another like stories in a building. Gods lived in the higher skies, while humans occupied the lower ones. Beyond the higher sky there was little described. Silence took the place of answers. In many traditions, silence itself was the acknowledgement of infinity. If words could not reach beyond the edge, then the edge was left undefined. For cultures that lived close to the sea, infinity was often experienced in the daily view of the horizon. Sailors were perhaps the first to feel in their bones what infinity meant. To sail away from land was to step into uncertainty. Was there a wall of water at the edge? A waterfall pouring into nothingness? A boundary where gods prevented mortals from passing? Myths filled the gap with sea monsters, great whirlpools and guardians of the edge. These stories were not simply meant to frighten. They were ways of shaping the infinite into something graspable. If the world was too vast, then perhaps a serpent coiled at its edge could make it feel smaller. Interestingly, even the myths that insisted on boundaries often left traces of infinity. The Babylonian Enuma Elish describes the creation of the world from a primeval sea. Before the gods shaped the earth, there was only endless water. The world may have been made finite, but it was born out of the infinite. This pattern repeats across cultures. Order arises out of chaos. A contained world emerges from something boundless. The finite is carved out of the infinite like an island out of an ocean. This tells us something about the human mind. Even when we built myths of edges, we couldn't quite erase the suspicion that beyond those edges lay something without end. Our stories reflect our need for both. We crave boundaries to feel safe. We acknowledge infinity because the world refuses to be boxed in completely. Think, too, of the way these myths functioned in daily life. A farmer in Mesopotamia didn't need to know whether the universe was finite or infinite. He needed to know when the river would flood. A sailor in Greece didn't need to calculate cosmic geometry. He needed to know whether his ship would return from the horizon. Myths answered those practical needs by placing limits on the world. But beneath the surface, the larger question always lingered. Could it really end? Could there truly be an edge? As societies grew more interconnected, myths began to blend. Travellers returned with tales of lands beyond the known maps. Each discovery pushed the supposed edge farther away. The horizon retreated again and again. The finite world of one culture was shown to be only part of a larger, possibly infinite whole. Yet myths adapted. New edges were imagined, new boundaries drawn. The process repeated endlessly. What's striking is how persistent the image of the edge has been, even in modern imagination. We no longer believe in a dome overhead, or a turtle carrying the earth, yet we still talk about the edge of the universe. The phrase is a reminder that our minds prefer limits, even when evidence points the other way. To describe the universe as finite is to describe it in terms our ancestors would recognize. To describe it as infinite is to step into the same unsettling space they once filled with serpents and gods. In these ancient myths, we can see the beginnings of the very paradox we are exploring. The world must end somewhere, and yet it cannot end. It must be finite, and yet it hints at infinity. Myth was humanity's first attempt to live with that contradiction. Science would come later, offering new answers, but the shape of the puzzle has always been the same. And so, when we read the old stories of domes, rivers, turtles, and voids, we're not just reading about superstition. We're reading about the human attempt to balance boundaries and endlessness. The myths may sound quaint now, but they are echoes of the same unease we feel when we step outside at night and realize we cannot see an end to the stars. The question of whether the universe is finite or infinite is not new. It has always been with us. What changes is the language we use to approach it. Where our ancestors used gods and monsters, we use mathematics and physics. But the emotional experience, the mixture of comfort and fear, The longing for edges and the pull of infinity remains unchanged. When myths gave way to more systematic thought, the question of infinity didn't disappear. It only changed its clothing. Instead of gods holding up the sky or serpents circling the sea, the puzzle of whether the universe could truly be endless began to live in philosophy. Ancient thinkers weren't content with stories alone. They wanted reasons, arguments, and principles that could stand up to scrutiny. And among the earliest questions they wrestled with was whether infinity could exist at all. Infinity was not a comfortable idea for the earliest philosophers. To them it was like a shadow at the edge of reason, something that tempted the imagination but refused to be pinned down. The Greeks especially became the first to frame infinity not as a myth, but as a concept that could be debated, tested with logic, and even feared. They asked whether infinity was real, or whether it was just a trick of the mind. Could something endless actually exist? Or was infinity only a word we used when we didn't know how to describe the vastness of things? One of the earliest to take up the question was Anaximander, a philosopher from the 6th century BCE. He introduced the idea of the apeiron, a Greek word that meant the boundless, or the indefinite. For him, everything in the universe came from this boundless source. It was not a god in the traditional sense, but it was something eternal, without limit, the origin of all things. The apeiron was both creative and destructive, producing the world and then reabsorbing it. What made this remarkable is that Anaximander was not simply telling a myth, he was proposing a principle. The universe was not resting on turtles or domes. It was rooted in something infinite, something without borders. The boundless was not decoration around the edges of the world. It was the foundation of the world itself. Other philosophers were less enthusiastic about infinity. Pythagoras and his followers, who saw mathematics as the key to reality, believed in harmony, ratios, and order. For them, the finite was elegant. Numbers could be counted, shapes could be measured, proportions could be balanced. Infinity, by contrast, was disorder. It resisted ratio. It undermined harmony. To say something was infinite was, in their view, to admit ignorance. And so, for the Pythagoreans, the infinite was something to avoid, even to fear. It was the mark of the undefined, the imperfect. Zeno of Elea, a student of the philosopher Parmenides, took this unease with infinity and turned it into a series of famous paradoxes. Perhaps you've heard of the one where Achilles races a tortoise. In the story, Achilles gives the tortoise a head start. By the time Achilles reaches the place where the tortoise began, the tortoise has moved a little farther ahead. By the time Achilles reaches that new spot, the tortoise has again moved slightly forward. This continues endlessly. Achilles keeps closing the gap, but he can never quite catch the tortoise. On the surface, this seems absurd. Of course, Achilles can outrun a tortoise. But Zeno's paradox forced people to confront the idea of infinite division. If space and time can be divided without limit, then how can motion ever be completed? Zeno's puzzles made infinity into a problem, something lurking inside the very structure of reality. Aristotle tried to clean up this mess. He distinguished between two types of infinity. One he called potential infinity, the kind you get when you can keep counting numbers without ever stopping. You never actually arrive at infinity, but you can always go further. The other he called actual infinity, the idea of something that is already infinite, fully complete in its endlessness. Aristotle accepted potential infinity as useful, even necessary, but he rejected actual infinity. To him, nothing could truly be infinite in reality. Infinity, in its complete form, could exist only in theory, not in the physical world. The cosmos, he argued, was finite. The heavens had an outer boundary, a sphere of fixed stars. Beyond that, there was nothing. This perspective influenced Western thought for centuries. For Aristotle, infinity belonged to mathematics and abstraction, not to the real universe. And because his works were so influential, the suspicion of infinity became deeply embedded in philosophy and later theology. Infinity was treated as dangerous, too vast to belong to the orderly world. But not everyone agreed. The atomists, like Democritus and Leucippus, imagined the universe as an endless void filled with countless atoms. In their vision, there was no boundary to space. Atoms collided, combined, and separated forever. There were not just one world, but many, infinite worlds, scattered across infinite space. Their cosmos was limitless in both size and number. For them, infinity was not a threat, but a natural conclusion. If the universe had no walls, then it could only be infinite. If atoms could not be destroyed, then there would always be more. Their vision was startlingly modern, though it was dismissed for centuries as too radical, too chaotic, too uncomfortably endless. Outside of Greece, philosophers in India also wrestled with infinity, though in very different terms. In some schools of Hindu thought, the universe was seen as eternal, cycling endlessly through creation and destruction. Time itself was infinite, with no true beginning or end. The idea of kalpas, vast cosmic cycles lasting billions of years, made the human lifespan seem smaller than a blink. In Jain philosophy, infinity was treated as a fundamental category. The cosmos, they argued, had infinite space, infinite souls, and infinite time. Unlike the Greeks, who feared infinity as disorder, Jain thinkers classified it carefully, describing different types of infinity as if sorting a collection. To them, infinity was not threatening but natural. It was woven into existence itself. In Buddhism, the concept of infinity took on another nuance. The Buddha discouraged speculation about whether the universe was finite or infinite, arguing that such questions distracted from the path to enlightenment. Yet Buddhist cosmology still described vast, countless worlds and unending cycles of rebirth. Infinity here was less about the geometry of space, and more about the boundlessness of existence and suffering. The infinite was both real and irrelevant at the same time. Back in the Western tradition, the tension continued. The Stoics imagined the cosmos as finite, but endlessly repeating. The universe would be consumed by fire and then reborn again and again without limit. Here, infinity took the form of recurrence rather than size. Time might stretch forever, but space remained contained. This idea reveals another way philosophers try to compromise with infinity. If you couldn't accept an infinite cosmos, you could accept infinite cycles. Boundaries were preserved, but eternity was still acknowledged. As philosophy moved into the Middle Ages, religious thinkers inherited these questions. Could only God be infinite? If so, could the universe also share in infinity? Or would that diminish the divine? Theologians often argued that only God was truly infinite, and that the created world was finite by design. Yet even within this view, debates emerged. Could an infinite universe better reflect the greatness of God? Or was infinity reserved for the divine alone? The arguments were not only logical but deeply spiritual. Infinity became a question of theology as much as philosophy. What we see in all of this is that the earliest philosophers were not just asking abstract questions. They were trying to reconcile the same tension our ancestors faced when looking at the sky. The world feels finite, but it also refuses to be contained. Myths explain this with domes and monsters. Philosophy tried to explain it with logic, categories, and arguments. The puzzle remained the same, but the language grew more careful, more deliberate. And so, the question lingered. Can infinity exist? If it does, is it only potential, never actual? Is it the void beyond the stars, the endless cycles of time, the countless atoms in the void? Or is infinity only a word, a symbol for something we cannot truly grasp? The fact that philosophers debated this 2,000 years ago, and that we are still debating it today, tells us something important. The human mind cannot quite let go of the infinite, no matter how uncomfortable it is. The earliest philosophers may not have solved the question, but they set the stage for everything that followed. Mathematics, science, and cosmology would take up the same puzzle in their own ways. Could the universe really be infinite, or must it be bounded? Could something be both finite and infinite at the same time? These debates did not end with Aristotle or the atomists. They only grew larger, and as we follow them forward, we will see how infinity moved from philosophy into the heart of science itself. When philosophy was still young and myths were still being told around firelight, people didn't need words like infinity or cosmology to experience the question. All they had to do was look up. The night sky has always been a mirror for wonder, a canvas so wide that it pulls the mind beyond itself. Long before anyone could measure distances to the stars, the sight of them was enough to make infinity feel close, intimate, something you could fall into just by staring too long. Even today, with city lights dimming much of the view, the feeling remains when we find a dark enough place. The stars stretch beyond counting, and for a moment, our minds brush against that old mixture of awe and unease. It is worth slowing down and picturing what it must have been like in a world before electricity, before pollution dimmed the skies. Every night the heavens would come alive in a way most of us rarely experience now. Thousands upon thousands of stars, brighter than most modern observers ever see, scattered from horizon to horizon. The Milky Way would cut across the sky like a river of light, not faint and ghostly but sharp, textured almost close enough to touch. To step outside after sunset was to step under something so vast and glittering that it felt both protective and overwhelming. The night sky was not a backdrop. It was an event, a presence, something that demanded attention. For ancient people, this endless view was not abstract. It was woven into their daily rhythms. Farmers marked the seasons by which constellations appeared overhead. Sailors steered their ships by the positions of stars. Priests and storytellers looked upward to read omens or to trace the paths of gods. The sky was practical as well as mysterious. But its practicality did not diminish its wonder. In fact, it probably deepened it. To rely on the stars for direction was also to be reminded that their number stretched too far to imagine. Each point of light was fixed enough to be useful, but numerous enough to be bewildering. The sky became both a tool and a riddle. For us today, infinity often lives in numbers. We talk about billions of galaxies, trillions of stars, distances in light years that outstrip comprehension. But before those numbers existed, the human sense of infinity came simply from the failure to count. Try pointing at the stars one by one. Very quickly you lose track. They scatter across your vision faster than your mind can hold them. Even if you counted every star you could see, the hazy band of the Milky Way would still loom above, uncountable, reminding you that some things resist being numbered. This was infinity in its most direct form. Not a definition, not a proof, just the overwhelming realization that the sky is too full to measure. What's striking is how personal this experience is. Stand under the stars, and the scale of the universe doesn't just feel large, it makes you feel small. Not in a dismissive way, but in a humbling one. You're one person, standing on one patch of earth, looking at something that does not end. The mind bends under the weight of it. Some feel comfort in this smallness, the sense that we are part of something grander. Others feel unease, the suspicion that our lives are only a flicker against the backdrop of an infinite stage. Both reactions are valid, and both are shaped by the same simple act of looking up. Cultures across the world built their first calendars from the sky, but they also built their first dreams. The constellations are proof of this. Humans looked at random clusters of stars and drew shapes. Hunters, lions, dragons, birds. They made the infinite into stories, patterns they could remember. A scattered cosmos became a kind of picture book, a set of familiar images that could be shared across generations. In this way, the night sky became not only a mirror of infinity, but also a mirror of imagination. By telling stories about the stars, humans carved meaning into endlessness. The infinite was still there, but it was softened, framed by narrative. Even so, the infinite could not be entirely tamed. No matter how many constellations were named, there were always stars left over, countless dots of light that refused to be woven into stories. The Milky Way itself resisted categorization. Some cultures described it as a path for souls, others as the spilled milk of gods, others still as a great river. But the sheer number of its stars kept it just beyond comprehension. You could name a few. You could never name them all. The gap between what could be ordered and what could not became a quiet reminder of infinity. There's also the way the night sky changes. Each season brings new constellations. The familiar patterns rise and fall, replaced by others, and yet the stars return again, cycling in rhythms that stretch beyond individual lifetimes. A child might learn the constellations one year, only to see them return decades later in the same position. This return is comforting, but it also gestures toward eternity. The stars are not rushing toward an ending. They simply go on, season after season, year after year, long after individual lives are gone. To watch them is to sense both finitude and infinity at once. Our days are short. The sky is long. The night sky also reveals infinity through depth. At first glance, stars seem sprinkled on a flat dome, but watch carefully, and you realize they're not all the same. Some are faint, some bright, some clustered, some alone. With a telescope, even a simple one, the illusion of flatness dissolves completely. Stars resolve into systems, nebulae into clouds of light years across. What once looked like a surface becomes a depth that stretches further the more you look. Infinity hides not only in number but in dimension. The sky is not a painting but a volume, filled with layers upon layers that never quite end. There is something almost paradoxical in the way the night sky reveals infinity. It shows itself not by being blank, but by being full. The more stars you see, the more convinced you become that there must be more beyond your vision. Darkness itself plays a role in this. Between stars, the blackness of the sky suggests that space continues, that beyond the last faint point of light, there is still more. The contrast between light and dark becomes part of the experience of infinity. The stars are proof of presence. The darkness is proof of absence. Together they create the impression that the universe has no end. This is not just an ancient experience. Even today, astronauts describe something similar when they look out at the Earth from orbit. Surrounded by stars, they speak of the overview effect, a shift in perspective that comes from seeing both the smallness of Earth and the vastness of the sky at once. It's the same feeling our ancestors must have had, magnified by the technology that lets us leave the ground. Infinity presses in, reminding us that boundaries are human constructions, not cosmic ones. The night sky also teaches us something about time. The light from stars does not arrive instantly. It travels across space for years, centuries, sometimes millennia before reaching our eyes. To look at a star is to look back in time. The more distant the star, the further back we see. Some of the stars we admire may no longer exist, their light only now arriving after their death. The sky is not only a mirror of infinity in space, but also in time. It stretches endlessly backward, offering glimpses of a past we can never reach. Infinity here is not abstract. It is visible, a stream of light flowing across ages to meet us. Even in modern cities, where light pollution hides most of the stars, people still speak of the rare nights when the sky clears. The sight of even a handful of stars is enough to evoke the same ancient wonder. Imagine then what it must have been like for people who lived under skies unspoiled by artificial light. For them, infinity was not an idea. It was a nightly encounter, as familiar as breathing, as inevitable as the setting sun. Every evening, they stepped into a world without boundaries, and every morning, they carried that sense of endlessness into their lives. The sky continues to hold this role today. Scientists may measure it, chart it, and model it, but ordinary people still use it as a mirror of emotion. Lovers walk under the stars to feel connected. Travellers gaze at the constellations to orient themselves. Children look up and imagine other worlds, perhaps even other beings staring back. The night sky remains an infinite canvas, not because it has changed, but because our minds are still drawn to the same questions it has always raised. Where does it end? Does it end at all? What lies beyond what we see? And so the sky remains one of the clearest mirrors of infinity. It does not answer the question of whether the universe is finite or infinite, but it makes us feel the question in our bones. The stars remind us of number without limit. The darkness reminds us of depth without end. Together, they create a paradox we cannot escape. The universe may be bounded, but it feels boundless. It may be measurable, but it resists being measured. It may be finite, but in the night sky, it looks infinite. When people first looked at the night sky, it seemed still. The stars appeared fixed in their positions, rising and setting with the rhythm of the Earth's rotation, but not rushing anywhere. For centuries, the heavens were imagined as steady, unchanging, a perfect ceiling above the restless ground below. It was natural to think that the universe was static, balanced in place. Even when telescopes revealed more detail, the assumption held. The stars were countless, but they were thought to be timeless, shining in an eternal stillness. The idea that the entire universe might be expanding was so strange, so counter to intuition, that it only began to be taken seriously in the last century. The story begins with light itself. When astronomers studied galaxies beyond our own, they noticed something peculiar. The light from those galaxies was stretched, shifted toward the red end of the spectrum. This redshift meant that the galaxies were moving away from us, and not just a few of them, almost all of them. The farther away a galaxy was, the faster it seemed to be receding. At first, this was bewildering, but slowly the pattern became clear. The universe was not static. It was expanding. This discovery changed everything. Suddenly, infinity was not only a matter of size, but of motion. If the universe was expanding, then what was it expanding into? Did that mean there was an edge, some boundary being pushed outward? Or was the expansion happening everywhere at once, with no outside at all? These questions reshaped cosmology, and reshaped the way we think about what it means for the universe to be finite or infinite. It helps to imagine the universe as a balloon. Not a balloon floating in space, but a balloon as space itself. If you draw dots on the surface of the balloon and then inflate it, the dots move away from one another. Each dot sees all the others receding, and the farther apart they are, the faster they seem to separate. This is what the redshift was telling us. Galaxies are not flying through space away from one another. Space itself is stretching, carrying them along. The balloon surface has no edge, no boundary, and yet it is finite. You can walk around it endlessly without ever finding an ending. This strange combination, finite yet unbounded, became one of the central insights of modern cosmology. The expansion also revealed something else. If the universe is growing, then it must once have been smaller. Follow the galaxies backward, and they converge. This led to the idea of the Big Bang, the moment when the universe began as a hot, dense state, and then expanded into what we see today. Here again, boundaries and infinity collided. Did the Big Bang happen at a point, with the universe growing into space around it? Or was the Big Bang the expansion of space itself, with no outside at all? If it was the latter, then the universe could be finite in age but still infinite in extent. Infinity was no longer simply about how far space stretched. It was tied to how space itself behaved. But there's another layer to the puzzle. The universe may be expanding, but we cannot see all of it. Our view is limited by the speed of light. Light takes time to travel, and the universe has only existed for a finite amount of time. That means we can only see as far as light has had time to reach us since the Big Bang. This defines what we call the observable universe. Beyond that, space may continue, perhaps infinitely, but we cannot know for sure because its light has not yet arrived. The horizon of sight is not a metaphor. It is a literal boundary, a circle around us beyond which we cannot see. And yet, it is not a wall. Galaxies beyond that horizon may exist, but their light is forever cut off from us by the expansion of space. In this sense, the universe is both finite and infinite at the same time. Finite because we can only observe a limited region. Infinite because there may be no edge beyond that horizon. We live inside a bubble of sight, with the vastness beyond forever hidden. It is a humbling thought. The stars you see at night are only a tiny part of one galaxy. The galaxy itself is only one of billions within the observable universe, and the observable universe may be only a fraction of the whole. What lies beyond we cannot say. It may be more galaxies, stretching without end. It may be a curved cosmos that eventually loops back on itself. It may even be regions so different from our own that we would not recognize them. The horizon does not just mark the edge of what we can see. It marks the edge of what we can imagine with certainty. The expansion also raises questions about the future. If the universe is growing, will it expand forever? Or will it slow down, perhaps even collapse back into itself? Observations suggest that expansion is not slowing but accelerating, driven by something mysterious we call dark energy. If that continues, then distant galaxies will recede faster and faster until their light can no longer reach us. Over unimaginable timescales, the night sky itself would grow emptier. Stars would fade, galaxies would vanish beyond the horizon, and we would be left in cosmic isolation. Infinity here is not only about distance but about loss. The universe would still exist, perhaps infinitely, but we would no longer be able to see it. This horizon is not fixed. It changes with time. As the universe grows older, light from farther away has time to reach us, revealing more of the cosmos. But at the same time, the acceleration of expansion means that some regions will slip permanently beyond our sight. The horizon becomes both a gift and a limit. It reveals more as time passes, but also hides more forever. To live in such a universe is to live with the paradox of partial knowledge. We can measure so much, and yet what we measure may always be only a sliver of an infinite whole. The expanding universe also challenges our intuition about edges. If space is stretching, then what is it stretching into? The balloon analogy tempts us to imagine space expanding into something larger, some outside void. But according to the best models, that is not the case. Space expands into itself. There is no outside, no surrounding emptiness. The question, what lies beyond the universe, may not even make sense. The universe is not expanding into something, it is the expansion. This is perhaps the hardest idea to hold in mind. Our senses want edges, want containers, but the universe refuses to provide them. Astronomers describe this with mathematics and careful terms, but the emotional experience is similar to what our ancestors must have felt. Looking up at the night sky, they saw something that refused to end. Now, with telescopes, we see galaxies fleeing into the distance, horizons we cannot cross, and the possibility of infinite space. The science has grown, but the feeling is the same. We are caught between the finite and the infinite, trying to live in a cosmos that seems to hold both at once. What makes this especially striking is that the expanding universe is not just a distant abstraction. It affects us here and now. The The very fact that we exist is tied to expansion. Without it, matter could not have cooled, galaxies could not have formed, stars could not have burned, planets could not have gathered, and life could not have emerged. The finite limits of our horizon, the infinite possibilities beyond it, and the expansion that carries both forward are all part of the same reality. Infinity is not somewhere else. It is here, woven into the space around us, shaping the conditions of our lives. When we think about the universe as expanding, and about the horizon of sight that defines our limits, we're reminded again of the central puzzle. Could the universe be finite and infinite at once? It seems that it can, finite in what we can observe, infinite in what may exist beyond, finite in the time it has been expanding, infinite in the possibilities it contains. The balloon keeps growing, and yet there is no outside. The horizon keeps shifting, and yet there is always something beyond. When we speak casually about something being finite, the meaning feels simple. A loaf of bread is finite because it can be eaten. A road is finite because it eventually comes to an end. A human life is finite because it has a beginning and an end. But in science, the word carries a weight far beyond these everyday uses. To call the universe finite, or even parts of it, is not just to say it ends somewhere. It is to ask how far it stretches, how much it contains, how it is shaped, and what it means for anything to have a limit in the first place. The word finite, in scientific contexts, has several shades of meaning. Sometimes it refers to size, as in a finite distance or a finite amount of matter. Sometimes it refers to time, as in a finite duration or a finite age. And sometimes it refers to properties that cannot be stretched indefinitely. Energies, speeds, temperatures, all bound by specific values that define how the universe works. To understand what it means to call the universe finite, we have to move carefully through each of these meanings, because each opens its own version of the puzzle. The first is size. Imagine you're standing on Earth and you ask, is this planet finite? The answer seems straightforward. Earth has a surface you can measure, a circumference you can calculate, a volume you can compare. It is finite because it is contained. Even though you can walk endlessly in circles without ever falling off an edge, the measurements of Earth are bounded. The surface area is large but not infinite. The mass of the planet can be determined. In this way, finite does not necessarily mean there is an edge you can fall from. It means there is a limit to what can be measured. You can map the entire globe, and at some point the map is complete. Now stretch that thought to the universe. If the universe were finite in size, then like Earth, it could be described in total. You could, in principle, measure its volume, its mass, its energy. You could map the whole of it, even if the map were unimaginably large. But this doesn't mean there would be an edge. Just as walking around Earth never brings you to a wall, a finite universe might have no boundary. Instead, space could curve back on itself, allowing endless travel within a closed but contained hole. This is one version of finite that cosmologists consider, not bounded by edges, but bounded in extent like the surface of a sphere. The second shade of finite is time. The universe, as far as we know, has a finite age. It began with the Big Bang around 13.8 billion years ago. That number may be enormous compared to human lifespans, but it is still a number. It is not eternity. It is not forever. There was, as far as we can tell, a time when the universe was not in its current form. This finitude in time is one of the most startling scientific discoveries of the modern era. For centuries, people assumed the universe was eternal, always existing as it does. The idea of a beginning was unsettling, almost unnatural, and yet the evidence of cosmic expansion, the traces of background radiation, and the observations of galaxies all point back to a moment of origin. The universe, in time at least, appears finite, but finitude in time raises its own questions. If the universe began, what came before? If time itself began with the Big Bang, then perhaps there is no before in any meaningful sense. But if time stretches further back, then the universe may not be finite in age after all. Science, in this sense, confronts the same puzzle that myths and philosophy did. To call the universe finite in time is to draw a boundary, and yet the mind rebels, asking what lies beyond the boundary. The third meaning of finite relates to physical properties. The universe has limits that govern its behaviour. The speed of light is finite. No matter how fast you go, you cannot exceed it. The amount of energy in a system is finite. Conservation laws dictate that energy is not created or destroyed but transformed. The laws of thermodynamics place ceilings on efficiency, on temperature, on what is possible within physical systems. In this sense, finite is not about size or time, but about constraint. The universe is not a wild, limitless playground. It is a place governed by finite values that give it structure. These finite properties are not small things. They are what make science possible. If the speed of light were not finite, then distances would lose meaning. If energy could be infinite, then order and chaos would collapse into nonsense. If time were infinite in both directions, then cause and effect might dissolve. It is the finitude of these properties that allows a cosmos to exist in any coherent way. Infinity may haunt the edges, but finitude rules the centre. Of course, to say something is finite in science is not always straightforward. Consider space again. The observable universe is finite because we can only see so far. But is the whole universe finite? We don't know. Current evidence suggests it might be flat on the larger scales, which could imply it stretches without end. Or it might be curved in ways that make it finite but without edges. The measurements remain uncertain. What we can say is that the part we see is finite. What we cannot see may or may not be infinite. The boundary here is not physical but observational. The concept of finitude also carries emotional weight. A finite life means mortality. A finite earth means fragility. A finite universe means that even the stars themselves may someday fade. Science uses the word carefully, mathematically, but for us, finitude is never just a technical matter. It touches how we think about meaning, purpose, and place. To hear that the universe is finite in age is not simply to receive information. It is to confront the fact that everything has a story with a beginning and perhaps an end. At the same time, finitude offers comfort. A finite problem can be solved. A finite space can be mapped. A finite lifespan can be cherished. The infinite overwhelms, but the finite allows understanding. Science thrives on finitude because it makes prediction possible. We measure, calculate, and model precisely because the universe follows finite rules. If everything were truly infinite in all respects, science might dissolve into mystery. The finite makes knowledge possible. Still, even within science, finite does not always mean what it first appears to mean. To say the universe is finite in time does not necessarily mean it will end. To say it is finite in size does not mean it has an edge. To say it is finite in properties does not mean it is simple. Finitude is subtle. It carries layers of meaning that shift depending on context. It can be comforting or unsettling, limiting or liberating. This subtlety becomes especially clear when we ask whether something can be finite and infinite at once. Mathematics provides clues here. A line segment on a circle is finite in length, but if you keep travelling around the circle, you can go on without end. The circle is finite in extent, but infinite in experience. Likewise, the surface of Earth is finite in area, but you can walk endlessly without finding a boundary. These examples hint at how finitude and infinity can coexist. Science often borrows such models when trying to describe the universe. The scientific sense of finitude, then, is not absolute. It is contextual. The universe is finite in age, but perhaps infinite in extent. The speed of light is finite, but space may expand without bound. Energy is finite within systems, but the transformations it undergoes may continue forever. Science embraces these nuances because the universe itself seems to demand them. To describe it as simply finite or simply infinite would be to ignore its complexity. When scientists use the word finite, they mean more than just an end. They mean measurable, bounded, constrained, describable. The finite is what we can grasp, even if grasping it reminds us of the infinity beyond. The finite is the edge of knowledge, the part we can hold in equations, the piece we can test and repeat. It is not the whole, but it is what allows us to begin. When scientists use the word infinite, it does not carry the same looseness it often does in everyday conversation. People sometimes say something is infinite when they really mean very large, like infinite patience or infinite possibilities. But in science, the word infinite is used carefully and sometimes reluctantly. To call something infinite is to admit that no limit exists, not just practically, but in principle. It means that no matter how far you measure, how long you wait, or how much you count, there will always be more. It is not simply very big. It is beyond all bounds. Infinity in science appears in several different contexts, and each one challenges our intuition in its own way. The first is the idea of infinite space. If the universe extends without end, then there is no edge, no wall, no final point where it stops. Galaxies may continue forever, scattered through limitless distances. In this sense, infinity is not just a number too large to calculate, it is a statement about the structure of reality itself. There is no border because there is no outside. The universe simply continues no matter how far you go. This vision of infinity is difficult to hold in mind. Our lives are bounded by beginnings and endings. Every road, every book, every breath has a limit. To imagine something without one is to step outside the framework of daily experience. And yet science does not dismiss this possibility. The evidence from cosmology suggests that the universe may be flat on the larger scales, which would mean it extends indefinitely. That does not prove it is infinite, but it keeps the door wide open. If the cosmos is truly infinite, then what we see through our telescopes is only a vanishingly small part of an unending whole. Another place where infinity enters science is in mathematics itself, which underpins all physical theories. Mathematicians distinguish between different sizes of infinity, some larger than others, some so vast they challenge even the imagination of specialists. When physicists use equations to describe the universe, infinity sometimes appears as a result. In certain models, values blow up to infinity, signalling a breakdown in understanding. Black holes are a famous example. At their centers, the equations suggest a singularity, a point of infinite density where space and time curve without bound. Whether such infinities are real or simply artifacts of incomplete theories is an open question. But the fact that infinity emerges at all shows how deeply it lurks in the heart of science. Time, too, can be infinite. If the universe continues expanding forever, then time itself will stretch without end. Stars will burn out, galaxies will fade, but the fabric of time will not stop. It will keep unspooling, even if all that remains is darkness and cold. This kind of infinity is almost harder to accept than infinite space. It asks us to imagine not just vast distances, but endless duration, an eternal future that stretches so far it dwarfs all history. And if time is infinite in the future, then we face the possibility of infinite versions of events, infinite outcomes, infinite chances for things to happen. Infinity in time multiplies existence beyond anything we can really grasp. Infinity also shows up in the very small. Quantum physics suggests that space and time may be divided into units, but until we know for certain, the possibility remains that they can be split without end. If so, then even a grain of sand would contain infinite divisions. Inside the finite, infinity would hide, this is not just an abstract puzzle. It affects how we understand particles, fields, and the very nature of reality. The infinite can live not only in the vastness of galaxies, but also in the tiniest corners of matter. It is important to note that scientists are cautious about infinity. In equations, infinity often signals a problem, a place where a theory breaks down. When values shoot to infinity, it usually means the model needs revision. Physicists joke that infinity is a signpost that reads, "You have gone wrong somewhere." Yet at the same time, infinity cannot be ignored. The idea keeps returning, whether in black holes, in the expansion of the universe, or in the unending nature of numbers. It seems to sit at the boundary of knowledge, taunting us with its refusal to be contained. Infinity in science also has practical consequences. Consider the question of whether the universe contains infinite stars. If it did, then in every direction, your line of sight would eventually land on a star. The sky would be bright everywhere, with no darkness at all. This puzzle, known as Olber's paradox, forced astronomers to rethink. The darkness of the night sky suggests that the universe is not infinite in both age and extent, or at least not uniformly filled with stars. Here, infinity is not just an idea. It is a testable hypothesis, one that shapes our understanding of why the night looks the way it does. There is also the unsettling possibility of infinite repetition. If space is infinite, then matter must eventually repeat itself. Somewhere, far beyond our sight, there could be another Earth, another you, living out a life almost identical to this one. And somewhere else, another version, slightly different. In an infinite universe, everything possible might not only happen once, but happen infinitely many times. This is one of the strangest implications of infinity in science, and one that stretches the imagination beyond comfort. And yet, despite all this strangeness, infinity is not treated as impossible. It is treated as something to be handled carefully, acknowledged when necessary, questioned when suspicious, but never dismissed outright. In this way, infinity is both a concept and a challenge. It asks us whether the universe can truly be endless, and whether our minds, evolved to handle the finite, can ever truly grasp what that means. Infinity also has a curious relationship with beauty and science. Equations that contain infinity often feel incomplete, but at the same time, the infinite inspires awe. The idea that numbers stretch forever, that galaxies may extend without end, that time may roll on eternally, these are not only intellectual puzzles, but sources of wonder. Infinity, in science, becomes a bridge between the measurable and the immeasurable, the knowable and the unknowable. This is perhaps why the word infinite carries so much weight outside science as well. We borrow it for emotions, for love, for imagination, because it feels larger than anything else we can say. But when science uses it, the word retains its literal force. It means without boundary, without end, without limit. To call the universe infinite is not poetry. It is a hypothesis about the nature of reality. And so, when scientists speak of infinity, they are not being casual. They are trying to describe something that resists description, something that stretches beyond what we can measure but not beyond what we can conceive. The infinite is always out of reach, and yet it is always pressing in, showing itself in equations, in horizons, in the vast silence of space. To understand what infinite means in science is to realize that we live surrounded by it, touched by it, even if we cannot fully hold it. When people first began to ask whether the universe was finite or infinite, they often imagined edges, walls, or domes. But as science advanced, it became clear that the more interesting question was not whether the universe had a border, but what shape it might have. The geometry of space itself could determine whether the cosmos is endless or contained, curved or flat, looping back on itself or stretching forever. This realization was one of the great revolutions of modern physics. Instead of picturing the universe as something sitting inside and outside, scientists began to ask what shape space itself might take, independent of anything beyond it. The idea that the universe has a shape comes from general relativity, Albert Einstein's great theory of gravity. According to this theory, space is not a rigid stage where events unfold. It is dynamic, bending and curving under the influence of mass and energy. Just as a heavy ball on a trampoline causes the fabric to dip, a massive star or galaxy causes space to curve around it. If local masses can bend space, then perhaps the whole universe has a large-scale curvature as well. The question became, what is the geometry of the cosmos? There are three main possibilities that scientists consider: flat, open, or closed. Each one is not just a technical description, but a vision of reality, a way of imagining what it means for the universe to exist. A flat universe is the simplest picture. Imagine drawing a triangle on a sheet of paper. The angles add up to 180 degrees, as expected. Parallel lines stay parallel. Distances can be measured with straightforward geometry. In a flat universe, the rules of Euclid, the ancient mathematician, still apply even on cosmic scales. If you send two beams of light perfectly parallel to each other, they will never meet. Space continues in every direction, without curve, without limit. A flat universe could be infinite in extent. It stretches on and on with no boundary, no looping, no closure. But flatness does not necessarily guarantee infinity. It could also mean the universe is finite but unbounded, depending on its topology. The surface of a torus, a donut shape, is technically flat in its geometry but finite in extent. You can walk around it endlessly, looping back without ever hitting an edge. So when cosmologists say the universe might be flat, they do not mean it is necessarily infinite. They mean the geometry is not curved one way or the other. Infinity is possible, but not required. An open universe is different. Here, space is negatively curved, like a saddle. If you draw a triangle, the angles add up to less than 180 degrees. Parallel lines eventually diverge. Space spreads outward, expanding in such a way that it never loops back on itself. An open universe is infinite by its very nature. It stretches forever, with no boundary, no closure, no possibility of looping around to where you started. In this vision, the universe is like an endless plane, curving outward in every direction. Expansion would continue eternally, galaxies receding faster and faster, horizons forever growing, but never enclosing the whole. A closed universe, by contrast, is positively curved, like the surface of a sphere. Draw a triangle, and the angles add up to more than 180 degrees. Parallel lines eventually meet. Travel in a straight line long enough, and you will return to where you started, just as a traveller on Earth can keep moving in one direction and eventually arrive back at the same place. A closed universe is finite in size, but it has no edge. There is no wall, no border, nothing to fall off. Instead, it loops smoothly back on itself. The whole cosmos would be like the three-dimensional equivalent of a sphere, vast beyond comprehension but bounded. These three possibilities, flat, open, closed, capture the range of what the universe might be. Each has profound consequences for how we think about infinity. A closed universe would be finite in extent, but infinite in travel, since you could keep going forever without finding a stopping point. An open universe would be truly infinite, stretching without end. A flat universe could be either, depending on its underlying structure. The shape is not just geometry, it is destiny. Scientists have tried to measure the curvature of the universe by observing the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in that radiation carry clues about the geometry of space. The results so far suggest that the universe is very close to flat. Not perfectly proven, but close enough that on the largest scales we can measure, the geometry appears Euclidean. This finding has led many to consider the possibility of an infinite universe, though the door remains open to subtler topologies that could still make it finite. The idea that space itself could loop back on itself is particularly intriguing. Imagine firing a beam of light into the cosmos. In a closed universe, that light would eventually return from the opposite direction, having circled the cosmos. You could, in principle, see the back of your own head if you waited long enough. The universe would be like a hall of mirrors, where light wraps around and creates multiple images of the same galaxy. Scientists have looked for such patterns, trying to see if the cosmos repeats itself in the sky. So far, no conclusive evidence has been found, but the search continues. Each of these shapes also affects how the universe evolves. An open universe, with its negative curvature, tends toward eternal expansion, never slowing, never stopping. A closed universe might eventually collapse back on itself in a big crunch, where expansion reverses and everything converges. A flat universe sits on the edge between the two, delicately balanced, where the fate depends on other factors like dark energy. The geometry does not only tell us about space, it tells us about the future of time. What is striking is how these scientific models echo the ancient intuitions of myths and philosophy. The closed universe resembles the old idea of a dome or a sphere enclosing reality, finite yet without edge. The open universe resembles the boundless chaos, the endless sea into which the world dissolves. The flat universe mirrors the desire for order, for something that can be measured with the simple rules we know. Science has replaced gods and monsters with equations and observations, but the shapes still carry the same emotional weight. The shapes of the universe also touch on the question of how infinity can coexist with finitude. A closed universe shows how something can be finite yet unbounded. An open universe shows how infinity can be a natural consequence of geometry. A flat universe shows how subtle the balance can be between the two. In each case, our intuition about edges and borders is challenged. The universe may not need an edge to be finite. It may not need boundaries to be infinite. Geometry itself holds the answers that feel as strange as any myth ever told. When scientists talk about the universe being flat, open, or closed, they are not merely drawing diagrams. They're asking what it means for space itself to exist. They're asking whether the cosmos is a finite whole we can in principle measure, or an infinite expanse that defies all boundaries. They're asking whether we live in a universe that loops back on itself like a great circle, or one that stretches endlessly, or one balanced perfectly between the two. These are not just technical questions, they're questions that carry the same wonder as looking up at the night sky, the same unease as contemplating the edge of the world. The shapes of the universe are the shapes of our imagination, given form through science. When we ask about the size of the universe, it is tempting to imagine a number, a distance we could measure if only our instruments were powerful enough. But in reality, the cosmos does not reveal itself so simply. What we call the universe may extend forever, or it may loop back on itself, or it may have a size we can only estimate. What we know for certain is bounded by something subtler than walls or edges. It is bounded by light. The speed of a light is finite, and the universe has a finite age. Those two facts together create a horizon, a limit to how far we can ever see. Beyond that horizon, no information has had time to reach us. This boundary is not made of matter, it is made of time itself. Imagine standing on a shore watching waves roll in. No matter how far the ocean stretches, you only ever see the waves that have reached the beach. The rest are still out there, but they have not yet arrived. The observable universe works in a similar way. Light travels at a fixed speed, about 300,000 kilometers per second, which sounds unimaginably fast until you compare it to cosmic distances. Even light, moving at that relentless pace, takes time to cross space. When you look at the moon, you see it as it was a little over a second ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at distant galaxies, you're looking millions or even billions of years into the past. The further you look, the further back in time you peer. Because the universe has existed for about 13.8 billion years, you might think we can see no farther than 13.8 billion light years. But expansion complicates this picture. While the light was travelling toward us, space itself was stretching, carrying galaxies farther away. As a result, the edge of the observable universe is much farther than 13.8 billion light years. It extends about 46 billion light years in every direction. That sphere, centred on us, is the maximum region from which light has had time to reach us since the Big Bang. Everything beyond remains hidden, not because it isn't there, but because the signals have not yet arrived. This is the cosmic horizon, the ultimate boundary of observation. It is not fixed. With time, new light continues to arrive, revealing more of the universe. But expansion places another constraint. Some galaxies are receding so quickly, carried by the stretching of space, that their light will never reach us. They are already beyond what is called the event horizon, a point of no return. Just as nothing can escape a black hole beyond its event horizon, nothing beyond the cosmic event horizon can ever send light our way. This means that parts of the universe are forever inaccessible, not because they are destroyed, but because expansion carries them beyond reach. The horizon, then, is double-edged. On one side, it promises discovery, as more light reaches us over time, gradually painting a fuller picture of the cosmos. On the other side, it promises loss as distant regions recede beyond communication, slipping permanently out of view. To live in such a universe is to exist between revelation and erasure, always learning more and yet always losing more. This boundary reshapes the way we think about infinity. The universe beyond the horizon may be infinite, but for us, it is effectively invisible. The observable universe is finite, measurable, a bubble we can chart. But that bubble may be only a tiny fragment of something without end. We live inside a sphere of light, knowing there is more beyond, but unable to ever confirm how much more. In this way, the cosmic horizon creates a paradox. We can measure the size of the observable universe with extraordinary precision, yet the total size of the universe remains unknown, perhaps unknowable. There is something profoundly human about this situation. Our ancestors looked at the horizon on land or sea and wondered what lay beyond. Now we look at the cosmic horizon and wonder the same. The scale is unimaginably larger, but the feeling is the same. Curiosity pushes against the limits of sight, even when we know those limits cannot be crossed. The horizon invites exploration, even if the journey is impossible. Astronomers study the horizon through the faint glow of the cosmic microwave background, the radiation left over from the Big Bang. This light has travelled nearly the entire age of the universe to reach us, carrying a snapshot of the cosmos when it was only 380,000 years old. Beyond that point, the universe was opaque, filled with hot plasma that scattered light. The microwave background is, in a sense, the farthest we can see with light, the edge of a visible wall, but even here the horizon is not final. We can probe beyond it indirectly, using neutrinos, gravitational waves, and mathematics. Still, the limit of direct vision remains. We cannot see past the first light. This limit does not diminish the wonder of what we can see. In fact, it amplifies it. To realize that every point of light in the sky is a relic from the past, every galaxy a messenger from billions of years ago, is to experience time and space intertwined in a single vision. The cosmic horizon is not a static boundary. It is a dynamic record of history, showing us how the universe has unfolded across ages. Each observation pushes us closer to understanding the whole, even as the whole recedes beyond reach. There is also the sobering realization that horizons are not only spatial but temporal. Just as there is a limit to how far back we can see, there may be a limit to how far forward any civilization can endure. If expansion continues to accelerate, as current evidence suggests, then distant galaxies will eventually slip beyond view. The night sky will grow emptier over eons. The cosmic horizon will shrink in practice, isolating us in a smaller and smaller island of stars. In this distant future, the universe will still be vast, perhaps infinite, but it will feel finite to those within it, cut off from all but their own local surroundings. The concept of the horizon also connects with the idea of perspective. The observable universe is always centered on the observer. From Earth, it forms a sphere around us. From another galaxy, the sphere would form around it. Every point in the universe has its own horizon, its own bubble of light. This means there is no single universal horizon, only local ones, overlapping and shifting. Infinity, then, is not uniform. It is filtered through perspective, revealed differently depending on where you stand. The cosmic horizon reminds us that our place in the universe is both central and insignificant. Central because we are at the center of our own bubble. Insignificant because every other point has the same right to claim the center. This relativity of horizons underscores the strangeness of infinity. The universe may contain uncountable galaxies, but we each see only a slice. The horizon is both a limit and a reminder of what lies beyond. It is both a barrier and an invitation. It is both finite and infinite, depending on how you look at it. And so, when we think about cosmic horizons, we're thinking not only about astronomy but about perspective itself. What we can see, what we cannot, and how both shape our understanding. The horizon does not resolve the question of whether the universe is finite or infinite, but it embodies the tension. It is finite in what it allows, infinite in what it hides. It is the universe reminding us that knowledge is always partial, and that mystery is built into the structure of reality. When people first began to wonder about the universe, the most natural question was, where does it stop? If something is vast, if it spreads in all directions, then surely there must be a point where it ends. A wall, a barrier, a border of some kind. Without one, the mind feels untethered. To live in a world without edges is unsettling, because every experience we have is framed by limits. We walk along a road and eventually reach a fence. We look at a lake and see its shore. We look at the span of a lifetime and know it has boundaries. So when we think about the universe itself, it feels impossible that it could lack an edge. And yet, science suggests that may be exactly the case. To picture a universe without an edge, we first have to set aside our ordinary instincts. It is easy to imagine space as though it were a box and the galaxies are scattered inside it. If you walk far enough, you would come to the end of the box, a final wall enclosing everything. But space is not a box. It is the fabric of reality itself. If the universe has no edge, that does not mean it is infinite in every way. It may mean that space is curved or connected in such a way that you can travel endlessly without ever finding a boundary. The simplest analogy is the surface of Earth. Stand on the ground and walk in one direction. No matter how far you go, you will never reach an edge. You may walk around the globe, but the surface does not stop. It is finite in area, measurable and complete, but it is unbounded. It has no wall, no brink, no cliff. A universe without an edge may function in the same way, except in 3 dimensions instead of 2. Travel far enough in one direction, and you might eventually return to your starting point, not because you reached a wall, but because space curves back on itself. This idea is deeply counterintuitive, and yet it resolves many puzzles. If the universe has no edge, then there is no need to ask what lies beyond. The question of outside vanishes, because outside has no meaning. Just as the surface of Earth is not sitting on top of something else, the universe may not need an external container. It is all there is, self-contained, looping, unbounded. It's important to notice that this does not mean the universe is infinite. A closed, curved universe can be finite in volume, just as Earth is finite in surface area. But it has no border, nothing to mark a final stopping point. The distinction between finite and infinite becomes subtler when you remove edges. A universe without boundaries blurs the line, showing how something can be measurable and yet endless in experience. There is another way to imagine this using the balloon analogy. Picture the surface of a balloon. It is finite but unbounded. As the balloon inflates, the surface expands, and every point moves away from every other. If you live on the surface, you can travel forever without finding an edge. The balloon has no border for those who live within it. The universe, in this analogy, is like the surface but in higher dimensions. It can be finite in content, yet infinite in traversal. Expansion only stretches it further, without ever producing a wall. This idea of a universe without edges challenges the way we think about journeys. On Earth, every path leads somewhere. Even if the road loops, you eventually return. But in a cosmos without borders, travel may not reveal new ground but repeat what already exists. There may be paths that loop back on themselves, like travelling across space and returning from the other side. In such a universe, what you see might not be unique. Galaxies could appear multiple times in different positions, reflections of themselves caused by the curvature of space. Astronomers have searched for such repetitions, clues that the universe wraps around. So far, none have been confirmed, but the possibility remains. Philosophically, a universe without an edge is both elegant and disconcerting. Elegant because it removes the awkwardness of asking what lies beyond the universe. Disconcerting because it undermines our sense of enclosure. We like boundaries, even distant ones. They make the world feel safe, contained. To live in a universe without edges is to live in something that feels unfinished, always open, never finally resolved. And yet, edges themselves carry their own difficulties. Imagine reaching the supposed edge of the universe. What would be there? A wall? A void? If it were a wall, what lies behind it? If it were a void, is the void part of the universe or beyond it? The very idea of an edge leads to contradictions. A universe without edges avoids these problems by redefining the whole. There is no beyond, there is only the universe. This shift in thinking also affects how we imagine infinity. An infinite universe suggests space stretches endlessly in every direction. But a finite, unbounded universe is different. It suggests that you can never find a border, but that the total content is still limited. You can circle endlessly, but you will always circle the same total space. Infinity in this sense becomes experiential, not structural. The journey never ends, even if the map is complete. The emotional weight of this is hard to overstate. For people who seek closure, the absence of edges is troubling. But for those who seek openness, it is liberating. It means the universe is not trapped inside something larger. It is self-sufficient, needing no outside. It is everything there is, and that is enough. Even modern cosmology does not fully settle this question. The data suggest that on large scales the universe may be flat, which could mean infinite, but it could also mean finite and unbounded, depending on the global topology. We simply do not know whether the universe is infinite in extent or finite without edges. What we do know is that we have never seen a sign of a border. Every observation points to continuation, not termination. For everyday life, the distinction may feel distant. Whether the universe ends somewhere or loops endlessly, the stars remain above us, galaxies remain scattered, light continues to travel, but the conceptual difference is enormous. If there is no edge, then the universe is not only vast but structurally strange. It is a place where our deepest intuitions about limits fail, where questions like, what lies beyond, dissolve into meaninglessness. In some ways, this resembles the transition from myth to philosophy, from domes to spheres, from boundaries to curves. The ancient idea of the heavens as a solid ceiling was replaced by Aristotle's spheres, and later by Copernicus's cosmos, and later still by Einstein's relativity. Each step has pushed the edge further away until finally the possibility emerges that there is no edge at all. The universe is not enclosed. It is unbounded, complete in its openness. The human mind may never be fully comfortable with this. We crave edges because they help us make sense of things. We like to know where something stops. A universe without edges denies us that comfort. But it offers something else in return. The chance to live in a cosmos that is whole without being closed, vast without being contained, endless without being infinite. One of the strangest truths revealed by science is that something can be boundless without being infinite, limited without having an edge. At first, the words seem contradictory. Boundless suggests freedom, endlessness, no restrictions. Limited suggests confinement, a total amount that cannot be exceeded. How can both descriptions apply to the same thing? And yet, the more closely we study the universe, the more this paradox seems to lie at its core. The best way to begin is with an example closer to home. Imagine again the surface of Earth. From where you stand, it seems to stretch in every direction. You can walk east forever, and the path never ends. You will never find a cliff where the world drops away into nothingness. In that sense, the surface is boundless. It has no edges, no borders, no final wall, and yet it is not infinite. The surface of Earth has a precise area. You can measure it, calculate it, even map every square kilometre. The total is finite. The paradox is resolved only when we realise that boundless is not the same as infinite. Boundless describes experience. Finite describes measurement. When applied to the universe, this distinction becomes profound. Space may be finite in extent, with a total volume that could in principle be measured. But if it curves back on itself, if it is closed in shape, then it is boundless. You could travel forever without ever hitting a wall. Like the surface of Earth, the universe could be complete but edgeless. This is not a trick of words, but a genuine possibility in modern cosmology. The paradox is real, limited yet unending, contained yet without boundaries. This idea unsettles us because it runs against instinct. When we think of something finite, we picture a box, a jar, a container. We assume limits come with edges. When we think of something infinite, we picture endless extension, no edges anywhere. But geometry shows us a middle ground, one that neither instinct nor language prepares us for. The finite can be unbounded. The boundless can be limited. The universe may exist in this space between categories, refusing to fit neatly into either side. Philosophers long before modern science struggled with this paradox. Aristotle believed infinity could not exist in the real world, but he also rejected the idea of an edge to the cosmos. His solution was to imagine the heavens as a set of spheres enclosing one another, finite in structure but without an outside. Centuries later, Kant would argue that both the idea of a finite universe and the idea of an infinite one led to contradictions. If finite, then what lies beyond? If infinite, then how can the mind grasp it? The paradox of boundless but limited was there even before Einstein gave us the mathematics to describe it more precisely. Science now offers a framework for this paradox in the form of curved space. A closed universe with positive curvature is like a three-dimensional sphere. Such a universe has a finite volume but no boundary. You could travel through it endlessly, looping back without ever encountering an edge. The words boundless and limited meet here, not as opposites, but as partners. The universe is limited in content but boundless in experience. What is remarkable is how this paradox appears in smaller ways throughout nature. Consider the inside of an atom. The electrons can only occupy certain energy levels. The system is finite in what is allowed. But within those constraints, the possibilities feel boundless. Or consider fractals, patterns that repeat endlessly at smaller and smaller scales. Each image on your screen is limited in resolution, but the mathematical pattern is boundless in detail. The interplay between finite and infinite is woven into the very fabric of reality, not only in the universe as a whole, but in the structures within it. The paradox also raises deep questions about meaning. If the universe is boundless but limited, what does that say about our place in it? On one hand, it suggests we live in a cosmos that is whole, self-contained, complete. There is no outside, no larger container holding it. On the other hand, it suggests we live in something that, while finite, can never be fully travelled, never fully exhausted in experience. We live in a world that is enough, but also a world that never ends. For some, this paradox is comforting. It means the universe is not infinite chaos, but structured, measurable, finite in content. For others, it is unsettling, because the lack of boundaries feels unnatural. The human mind is used to edges. To live in a universe without them, even a finite one, is to live in something that defies our most basic categories. The paradox is not just scientific, but psychological. It forces us to live with contradiction. This contradiction appears even in language. When we say the universe is boundless, we often mean it is infinite. When we say it is finite, we often mean it has edges. But the reality may not match the words. The universe may be finite without edges, boundless without infinity. Our categories bend and strain, trying to describe something that resists description. This is why so many cultures have resorted to metaphor, why myths spoke of domes and oceans, why philosophy spoke of spheres and voids. The paradox demands imagination, not just calculation. Even today, scientists must tread carefully when speaking about these ideas. If the universe is finite, people want to know what lies beyond. If it is infinite, people want to know how that can be possible. If it is boundless but limited, people struggle to picture what that means. Analogies help. The surface of Earth, the balloon, the sphere. But none of them are perfect. Each is an attempt to make the paradox accessible, to show how the impossible can be possible. The paradox also deepens when we consider time. If time began with the Big Bang, then it is finite in duration. But like space, it may be unbounded. The future stretches forward without limit, even if the past has a boundary. In this way, time too can be boundless but limited, finite in age but infinite in possibility. The paradox is not confined to space. It touches every dimension of reality. And so we live in a universe where the most natural categories fail. Boundaries exist in daily life, but the cosmos may have none. Infinity exists in mathematics, but the universe may not require it. Instead, we're left with something in between, something that is boundless yet limited, finite yet without end. This is not a flaw in science. It is a reflection of how strange reality can be, how far it exceeds the simplicity of human intuition. Infinity can feel like a word for the imagination rather than a number for science. People use it in casual ways. An infinite amount of time, an infinite number of possibilities, infinite patience. But in mathematics, infinity is not just a vague gesture toward largeness. It is a carefully studied idea with rules, hierarchies, and even different sizes. When mathematicians look at infinity, they do not see a single thing. They see a landscape, a whole structure of infinities, each bigger than the last. And this is where the mind begins to stretch beyond anything it was designed for. To begin with, infinity is not treated like ordinary numbers. You cannot simply place it at the end of the number line, as though counting 1, 2, 3 and so on forever would eventually bring you to infinity itself. Infinity is not a final destination. It is the idea that there is no final destination. You can count without stopping, and the sequence never ends. Infinity is the absence of a stopping point, not a point you eventually reach. This was already puzzling to the ancient Greeks. Aristotle distinguished between potential infinity, like the endless act of counting, an actual infinity, a completed infinite quantity. He accepted potential infinity. After all, you can always add one more to any number. But he rejected actual infinity, because to him, nothing real could be truly infinite. Numbers could stretch without end, but infinity itself could not be captured as a completed thing. For centuries, this view held sway. Infinity was treated as a concept, not as something you could work with directly. That changed in the late 19th century, when the mathematician Georg Cantor began to explore infinity more boldly. He showed that infinity could be studied not as a vague idea, but as a precise mathematical object. Cantor made the radical claim that infinities could be compared, and that some infinities were larger than others. At first, this sounds impossible. If something is infinite, how can it be bigger than another infinity? But Cantor's work revealed a hidden richness to the concept, something that shocked his contemporaries and still amazes mathematicians today. Consider the simplest infinity, the counting numbers 1, 2, 3, and so on. This set is infinite because you can keep adding without ever running out. Cantor called this infinity countable. It is infinite, but you can list its members one by one in an ordered sequence. Even if the list never ends, the process is straightforward. This is the smallest kind of infinity. Now consider the real numbers, the numbers that include fractions, decimals, irrationals, like the square root of 2 or pi. Cantor showed that this infinity is larger than the infinity of counting numbers. You cannot list all the real numbers because between any two, no matter how close, there are infinitely many more. The set of real numbers is uncountable, an infinity that dwarfs the infinity of counting numbers. Suddenly, infinity is not a single concept but a hierarchy. There is infinite, and then there is more infinite. Cantor's discovery caused an uproar. Some mathematicians and philosophers resisted the idea, insisting it was nonsensical. How could there be different sizes of something that is already beyond all limits? But the logic was airtight. Cantor even proved it with his famous diagonal argument, showing that any attempt to list the real numbers will always leave some out. Infinity, he demonstrated, comes in layers, like steps rising into the clouds, each one higher than the last without end. Once this door was opened, infinity grew even stranger. Cantor and others showed that there are infinitely many infinities, each larger than the one before. The landscape of infinities stretches upward without bound, a tower that cannot be climbed to the top because there is no top. This realization reshaped mathematics and indirectly science. It showed that infinity is not simply a synonym for very big. It is a structured idea, a field of study in its own right, with laws as precise as those of algebra or geometry. In science, infinities often appear as warnings. When an equation spits out infinity as an answer, it usually means the theory is broken down. A black hole singularity, for instance, is a place where density becomes infinite in the mathematics, but many physicists believe this signals the need for a new theory. Not that nature literally creates infinite values, and yet at the same time infinity is indispensable. Without it, calculus would not exist. Without calculus, modern physics would collapse. Infinity, paradoxical as it is, lies at the foundation of the tools we use to describe the universe. Calculus itself is built on the idea of infinity. To calculate areas under curves, or to describe motion, you divide things into smaller and smaller parts, approaching infinitely small slices. These infinitesimals are not numbers you ever reach, but limits you approach. The mathematics works because infinity is allowed to guide the process. Without infinity, the precise predictions of physics would be impossible. The orbit of planets, the spread of heat, the behavior of waves, all depend on calculations that use infinity at their core. There is also the curious fact that infinity can produce counterintuitive results. For example, Hilbert's Hotel, A thought experiment introduced by the mathematician David Hilbert shows how strange infinity behaves. Imagine a hotel with infinitely many rooms, all occupied. A new guest arrives. At first, it seems impossible to make room, since every room is full. But because the hotel is infinite, you can simply move the guest in room 1 to room 2, the guest in room 2 to room 3, and so on, freeing up room 1. Suddenly, the hotel that was full has space for more. In fact, you can repeat the process to make room for infinitely many new guests. Infinity is never truly full. This paradox illustrates that infinite sets follow rules utterly different from finite ones. When we apply this to the universe, the implications are staggering. If space is infinite, then there may be infinitely many galaxies. If time is infinite, then there may be infinitely many futures. If infinities come in different sizes, then the cosmos may hold structures of endless complexity, beyond even the largest numbers we can conceive. The mathematics of infinity shows us that the universe, if infinite, is not merely bigger than we imagine. It is bigger in ways that defy imagination altogether. What makes this even more striking is how infinity feels simultaneously familiar and alien. Everyone understands in a basic sense that you can always add one more when counting. Children quickly grasp that numbers never stop, and yet, when mathematics pushes this simple idea to its limits, it becomes a concept so strange it reshapes entire fields. Infinity begins as common sense and ends as the most profound abstraction. It is also worth noting that infinity is not always comfortable. Cantor himself struggled deeply with the implications of his discoveries, both mathematically and personally. He believed he was uncovering truths of the highest order, perhaps even touching on the infinite nature of God. But many of his contemporaries rejected his ideas, leaving him isolated. Infinity for him was both a triumph and a torment. It shows how the concept does not only stretch the boundaries of mathematics, but also the boundaries of the human spirit. When we talk about infinity in science, we are not speaking casually. We are invoking a concept with centuries of struggle, discovery and debate behind it. Infinity is not a single thing but a whole universe of ideas, each larger than the last, each challenging us to think beyond edges and limits. It is bigger than big, stranger than strange, and yet it sits quietly at the heart of the equations that describe our world. When we think of infinity, our minds usually turn outward, toward the vastness of space or the endless march of time. We imagine galaxies without number, distances without end, futures stretching on forever. But infinity does not only live in the enormous. Sometimes it hides within the small, nested inside patterns that repeat themselves in ways so intricate that no matter how close you look, there is always more to see. This is the strange world of fractals, where the infinite resides within the finite, and where a single shape can contain endless detail. The word fractal was coined in the 20th century by the mathematician Benoit Mandelbrot, but the idea is far older, woven into the patterns of nature that people have noticed for centuries. A coastline, for example, looks jagged from above. When you walk along it, the jaggedness persists, now in the rocks and inlets. Zoom in further, and you find more irregularity in pebbles and grains of sand. The boundary between land and sea is never smooth. It reveals new detail at every scale. The length of the coastline even seems to depend on how closely you measure it. The closer you look, the longer it becomes, as each new level of detail adds length. In principle, the process never ends. The coastline is finite in extent, but infinite in detail. Fractals make this idea precise. A fractal is a shape that repeats itself across scales. Zoom in, and the same pattern appears again, often slightly transformed but recognizable. The Mandelbrot set, perhaps the most famous fractal, illustrates this vividly. It is a mathematical shape defined by a simple equation, yet when visualized, it reveals endless complexity. No matter how far you magnify a portion of the Mandelbrot set, New structures emerge, spirals and tendrils and miniature copies of the whole, repeating endlessly. The boundary of the set is infinitely detailed. It is finite in area, fitting neatly within a small region of the plane, but its perimeter is infinite, so intricate that it can never be fully traced. This is the paradox of the infinite within the finite. The whole object is bounded, contained, measurable. And yet within those bounds there is endlessness. The infinite does not require vastness. It can live inside smallness, hidden in layers of self-similarity. A fractal teaches us that infinity is not only a question of size, but of structure. Nature is full of fractal-like patterns. Fern leaves split into smaller leaves that resemble the whole. Trees branch in repeating patterns, each branch a miniature version of the trunk. Rivers divide into tributaries, each one echoing the structure of the larger flow. Even the networks of blood vessels in the body follow fractal patterns, branching into smaller and smaller vessels until they reach the tiniest capillaries. Clouds, mountains, lightning bolts, all show the same recursive structure. Infinity is not just in the stars. It is in the way water carves rock, the way plants grow, the way light forks across the sky. This idea that infinity can live inside the finite has implications beyond aesthetics. It reveals something about the nature of complexity. Simple rules, repeated over and over, can generate patterns of infinite richness. A fractal is not made from complicated instructions. It is made from iteration, the repetition of a process. Add, square, repeat, and infinity emerges. This challenges our intuition, because we often assume that complexity requires complicated causes. Fractals show us the opposite. Infinity can arise from simplicity. Mathematically, fractals also blur the line between dimensions. A smooth line is one-dimensional. A filled shape is two-dimensional, but a fractal can live somewhere in between. The jaggedness of a coastline, for example, means it has a fractional dimension. It is more than a line, but less than a surface. This fractional dimension is part of what gives fractals their infinite detail. They are caught between dimensions, forever refusing to settle neatly into one or the other. Philosophically, fractals invite us to rethink what infinity means. We are used to thinking of infinity as unreachable, something always out there, beyond our grasp. But fractals bring infinity into reach, showing us that endlessness can be contained in the palm of a hand. Look at a Romanesco broccoli, with its spirals upon spirals, each head a miniature version of the whole, and you are staring at a natural fractal. Infinity is right there, not in distant galaxies, but in vegetables on the dinner table. The infinite within the finite becomes tangible, visible, edible. This challenges the way we divide the world into categories. Finite and infinite no longer sit at opposite poles. They overlap, interpenetrate. A shape can be finite in extent but infinite in structure. A pattern can be bounded but inexhaustible. The categories dissolve, leaving us in the paradoxical space where infinity hides inside limits. The emotional impact of this is subtle but powerful. There is comfort in knowing that infinity is not always distant and overwhelming. It can be close, familiar, even ordinary. The spiral of a seashell, the branching of frost on a window, the swirl of a galaxy, all share the same recursive beauty. Infinity is not only a vast abyss, it is a pattern repeating in front of our eyes. At the same time, fractals remind us of how small we are. No matter how much we magnify a fractal, there is always more detail. No microscope is powerful enough to reach the end. The infinite recedes as we approach it, always offering more, always remaining just out of reach. This endlessness within the finite mirrors the endlessness of the cosmos. Both show us that infinity does not need to be somewhere else. It is woven into the very structure of things. Fractals also suggest a new way of thinking about the universe itself. If the cosmos is structured fractally, with galaxies clustering in patterns that repeat at different scales, then infinity may live not only in size but in arrangement. Observations of large-scale structures hint at this possibility, with galaxies forming webs and filaments that resemble cosmic fractals. Whether this pattern continues endlessly is unknown, but the suggestion is tantalizing. Perhaps the universe is fractal in its very bones, infinite within finite clusters, repeating across scales beyond comprehension. The idea of infinite within finite also plays a role in art, philosophy, and even spirituality. Artists use fractals to create images that feel both ordered and chaotic, both bounded and endless. Philosophers use them as metaphors for the mind, which can be finite in capacity but infinite in creativity. Spiritual traditions sometimes see fractal patterns as reflections of deeper truths, where the part mirrors the whole and the whole contains the part. Infinity becomes not only a mathematical idea but a way of understanding existence. And so, when we talk about the infinite within the finite, we are not only speaking of equations or images on a screen, we are speaking of a way of seeing the world. Every branching tree, every jagged rock, every swirling cloud is a reminder that infinity is not always far away. Sometimes it is right here, hidden in patterns we have been looking at all along. When we talk about infinity, most of the time we're thinking about space. We imagine endless distances, galaxies without number, horizons that stretch beyond sight. But infinity is not only a question of space, it is just as deeply a question of time. If the universe exists now, and if it continues to exist tomorrow and the day after and the year after, then what about 1 billion years from now? What about 1 trillion? Does time itself ever stop? Or does it stretch forward endlessly, offering a future so vast it cannot be measured? To ask if the universe is infinite is also to ask whether time applies infinity to the future. At first glance, the idea of infinite time seems simple. Just as you can always add one more number when counting, you can always imagine one more moment after this one. If you are alive today, tomorrow will come. If tomorrow comes, then the day after will come too. The sequence appears to have no natural endpoint. Even if individuals pass away, time itself marches forward, indifferent to beginnings and endings. The flow of time feels infinite because it never stops. But when we examine it more closely, the question becomes far stranger. For one thing, we know the past has not been infinite. The Big Bang set a beginning for the universe about 13.8 billion years ago. That means time itself, at least as we know it, has a finite age. This discovery shocked earlier thinkers who assumed the cosmos was eternal. But if time had a beginning, does it also have an end? Or could the arrow of time extend forward forever, even if it began in the past? Science offers several possibilities. One scenario is that the universe continues expanding forever, driven by dark energy. In that case, time would stretch forward without end. Stars would burn out, galaxies would drift apart, and eventually even atoms might decay, but the flow of time would not stop. There would always be another moment, even if the universe grew emptier with each passing age. Time would be infinite in the future, even if it was finite in the past. Another scenario is that the universe might eventually collapse. If expansion were to slow and reverse, galaxies would begin falling back together, stars and planets would be consumed, and the cosmos would end in a big crunch. In that case, time would be finite not only in the past but also in the future. The arrow of time would have both a beginning and an end. Existence itself would be framed between two boundaries like the pages of a book. Still another scenario is cyclical. Instead of a single beginning and end, the universe might expand, collapse, and expand again, repeating endlessly. Time would not be infinite in one direction, but infinite in cycles. Each cycle would be finite, but the process as a whole would never end. The universe would have no final moment, only eternal repetition. Infinity would live in recurrence, not in unbroken duration. These scenarios remind us that infinity in time is not a simple yes or no. It depends on the fate of the cosmos, on the physics that governs expansion and energy, and on how we define time itself. It also reminds us of the deep paradox of infinity. If the future is infinite, then every possibility that can happen will happen, not just once, but endlessly. If time stretches without limit, then versions of events may repeat, or variations may play out forever. Infinity in time multiplies existence beyond imagination. This possibility is unsettling. Imagine yourself 1 trillion years in the future. By then, Earth will be long gone, the sun extinguished, galaxies receding faster than light. Will there still be a clock ticking somewhere? Will there still be a concept of next moment? If time is infinite, then the answer must be yes. Even in a universe emptied of light, time itself may continue. It would not need matter or energy to mark it. It would simply be the ongoing possibility of sequence, of one thing after another. Time would be stripped of events, but not of existence. For us, the personal connection to infinite time is mortality. Each human life is finite. We measure our days and years, knowing they will not last forever. Against this finitude, the thought of infinite time is overwhelming. Our lives are small sparks, brief against the backdrop of eternity. Yet in another way, infinite time offers comfort. Even if we do not last, something does. The universe continues. The story does not stop with us. Infinity in time means there is always more beyond. Philosophers have long wrestled with this tension. Some saw infinite time as essential. Without it, they argued, the universe would be incomplete. Others saw infinite time as absurd because it implied that events could repeat infinitely many times, leaving no room for novelty. Theologians added another layer, asking whether only God could be eternal or whether the universe shared in that eternity. In each case, the question of infinite time was not abstract. It was tied to meaning, to mortality, to the search for permanence in a fleeting world. Modern physics adds yet another twist. Time, it seems, is not a universal river flowing the same everywhere. Relativity shows that time is relative to motion and gravity. Clocks tick at different rates depending on how fast you move or how close you are to massive objects. This means that the question of infinite time is not simple. Whose time? Measured how? Infinite in which frame of reference? The more we learn, the more slippery the concept becomes. Infinity in time may not be uniform. It may depend on perspective. There is also the possibility that time itself is an emergent property, not a fundamental part of reality. Some theories suggest that time arises from deeper laws, from entropy or quantum states. If that is true, then infinite time may not make sense in the way we think it does. What we experience as the passage of moments might not be fundamental at all. Infinity, then, would belong not to time itself, but to the underlying reality from which time emerges. And yet, even with all these complications, the simple intuition remains. The future feels open. There is always another tomorrow, always another step forward. Even if the universe is finite in age, the arrow of time feels boundless in its forward motion. To imagine an end to time is harder for the human mind than to imagine its infinity. The thought that time could simply stop, that there could be no next, feels unnatural, almost impossible. Infinity in time may be terrifying, but finitude in time feels even stranger. This reveals something about how deeply we are tied to sequence. Life is lived moment to moment, and those moments have always come. Birth, growth, change, decay, they all unfold in time. Our experience of reality is inseparable from its passage. Infinity in time, then, is not just a cosmological question. It is a reflection of how reality feels to us. If space shows us the vastness of the universe, time shows us the vastness of existence itself. Both raise the same paradox. Both bring us face to face with infinity. When we think about infinity, our minds tend to look upward, outward, and forward. We imagine the endless stretch of galaxies, the unbroken future of time, the possibility of limitless horizons. But infinity does not only live in what is vast, it may also live in what is small. If we look inward, past molecules, past atoms, past the particles that form matter itself, we arrive at the strange territory of quantum physics. And here, at the smallest scales, the question of infinity arises in new and unsettling ways. The quantum world is not like the everyday world. In daily life, things have positions, speeds, and boundaries. A chair sits in one place, a ball rolls with a measurable velocity, a tree occupies a clear space. But in the quantum world, certainty dissolves. Particles behave like both particles and waves. Positions blur into probabilities. The act of observing changes what is observed. Instead of firm edges, the quantum world offers shifting possibilities. Infinity slips in not through distance but through multiplicity. One way infinity enters quantum theory is through the idea of divisibility. In classical physics, space and time were thought to be continuous, divisible without end. You could take a distance and cut it in half, then cut the half in half again, continuing forever. Infinity lived in the endless possibility of division. Quantum mechanics challenges this. At very small scales, there may be limits. The Planck length, about 10 to 35 meters, is often considered the smallest meaningful unit of space. Below this, the very concept of distance may lose meaning. The same applies to time, with the Planck time setting a possible limit. If these limits exist, then infinity in division ends. But if they do not, then even the smallest particle contains endless layers, infinite in its structure. The debate is ongoing, unresolved, balanced between finite and infinite. Another way infinity appears is in the behavior of quantum fields. In quantum field theory, every particle is an excitation of an underlying field that extends through all space. These fields have energy even in their lowest state, known as the vacuum. Calculations of this vacuum energy sometimes produce infinities, values that blow up without bound. Physicists use a process called renormalization to handle these infinities, trimming them into finite predictions that match experiments. But the fact that infinity appears at all is troubling. It suggests that our theories, powerful as they are, may be incomplete. Infinity lurks in the equations, hinting at deeper truths we have yet to uncover. Quantum mechanics also introduces infinity through possibility. A particle does not have a single path. It has all possible paths, each with a probability. When Richard Feynman developed his path integral formulation, he showed that to calculate the behavior of a particle, you must consider every possible trajectory, from the ordinary to the absurd. A particle moving from one point to another does not simply take one route. In the mathematics, it takes all routes, an infinite set of possibilities, with each contributing to the final outcome. Infinity here is not in space or time, but in the branching of potential. This branching becomes even stranger in interpretations of quantum mechanics that suggest parallel universes. In the many worlds interpretation, every quantum event splits reality into multiple outcomes. If a particle can go left or right, then in one world it goes left, and in another it goes right. Each choice creates a new branch, a new universe. If this interpretation is correct, then infinity multiplies in ways almost impossible to imagine. Every event spawns countless futures. Every moment generates endless variations. The universe is not a single story, but an infinite library of stories, each playing out in parallel. Even without branching universes, quantum mechanics suggests infinities of possibility. Consider a simple quantum system, like an electron in an atom. The electron does not sit in one orbit like a planet around a star. It exists in a cloud of probability, spread out across space. There are infinite points where it might be found, infinite states it might occupy. The wave function describing it contains this infinity within its structure. Measurement collapses the possibilities into one outcome, but the underlying mathematics always carries the infinite branching of what could be. This tension between finite outcomes and infinite possibilities mirrors the paradoxes of the cosmos. At large scales, the universe may be finite but boundless. At small scales, particles may have finite outcomes but infinite potentials. Infinity creeps into both ends of the spectrum, meeting in the middle where our finite human lives unfold. Quantum theory also raises questions about the role of information. Some physicists argue that information can never be destroyed, not even in black holes. If that is true, then the total information content of the universe may be infinite, always preserved, never lost. Others suggest there may be limits, caps on how much information can be stored in a region of space. This debate ties directly into infinity, because it asks whether knowledge itself has an upper bound, or whether it stretches endlessly, hidden in the fine details of quantum states. One of the most unsettling appearances of infinity in quantum theory comes from singularities. At the center of black holes where gravity and quantum mechanics collide, equations suggest values go to infinity. Density becomes infinite. Curvature of space-time becomes infinite. This cannot be the final truth, most physicists agree. It means our current theories fail at that point. But still, infinity sits there in the mathematics, like a warning sign we cannot ignore. It tells us that the smallest scales may conceal not resolution but endlessness, not simplicity but complexity beyond comprehension. And yet, despite all this strangeness, the quantum world is not chaos. It is structured, predictable, tested in experiments with astonishing precision. Quantum mechanics allows us to build technologies, from lasers to computers to medical imaging. It works, even when infinity hides in the equations. This is part of the paradox. Infinity is both a threat to understanding and the source of understanding. Without it, the theories might collapse. With it, the theories demand revision. For us, the infinite possibilities of the quantum world invite reflection about existence itself. If every particle carries infinite potential, then every moment of our lives may carry more possibility than we realize. If reality itself branches endlessly, then there may be versions of us living out countless futures, infinite in their variety. Infinity, in this view, is not just a distant abstraction. It is part of the ground beneath our feet, part of the fabric of every moment we live. The smallest scales, then, mirror the largest. Infinity lives both in the galaxies beyond sight and in the quantum fields beneath matter. It lives in the endless branching of possibility, the unbroken divisibility of space and time, the mathematics that explodes into values too large to handle. The universe, whether vast or tiny, refuses to stay bounded. It offers infinity in every direction, even when we try to confine it to the smallest of scales. The word universe has always carried a sense of finality. It means everything, all that exists, all that has ever existed, all that will ever exist. By definition, it feels complete, singular, absolute. But modern science has begun to ask a startling question. What if our universe is not the only one? What if there are others, countless others, perhaps even an infinite number of them? This is the idea of the multiverse, a possibility that stretches the imagination to its breaking point. The notion of multiple universes is not entirely new. Philosophers and storytellers have toyed with it for centuries. Ancient myths sometimes spoke of layered worlds or parallel realms where gods and spirits lived. Hindu cosmology describes endless cycles of universes being created and destroyed, one after another. In Buddhism, there are descriptions of countless world systems existing simultaneously. Even in Western philosophy, thinkers speculated about other worlds, invisible to us but real in their own right. The human mind has always been drawn to the possibility that our universe is not alone. What is different now is that physics has given the idea new weight. Several lines of scientific thought have led to versions of the multiverse, each arising from attempts to solve other puzzles. The first comes from the infinite nature of space itself. If the universe is truly infinite, then matter must eventually repeat. With only so many ways to arrange particles, an infinite universe would contain every arrangement, and not just once, but infinitely many times. Somewhere, unimaginably far away, there could be another Earth, another solar system, another version of you sitting and listening to these words. In fact, there could be infinitely many such versions, each with small differences, each living out alternate stories. Another version of the multiverse arises from cosmic inflation, the rapid expansion of space thought to have occurred in the first moments after the Big Bang. According to some models, inflation did not end everywhere at once. Instead, it may have ended in patches, each bubble of space forming its own universe with its own physical laws. If this is true, then our universe is just one bubble in an infinite froth, each bubble a universe in itself. Some may be like ours, with stars and galaxies. Others may be utterly alien, with different particles, different forces, perhaps even different dimensions. The multiverse here is not just repetition but variation, endless diversity across infinite space. Quantum mechanics offers yet another path to the multiverse. In the many worlds interpretation, every quantum event splits reality into branches. When a particle has a chance of going left or right, the universe divides, creating two outcomes that exist in parallel. If this interpretation is correct, then every choice, every random event, every coin flip generates new universes. The number of worlds grows exponentially, branching infinitely as time unfolds. In one, you turned left on your walk today. In another, you turned right. In one, you spoke a certain word. In another, you remained silent. The multiverse in this view is not distant or abstract. It is intimately tied to every moment of existence. String theory, too, suggests the possibility of multiple universes. Its equations allow for many possible configurations of dimensions and physical constants. Some physicists argue that each configuration could correspond to its own universe. The number of possibilities is enormous, perhaps on the order of 10 and 500. That is not infinity, but it is a number so large that it may as well be endless for human imagination. If all of these possible universes exist, then our own is only one among an incomprehensible multitude. The multiverse challenges our sense of uniqueness. For centuries, humans believed Earth was the center of the cosmos. That idea fell away when we learned Earth was one planet among many. Later, we learned our sun was one star among billions in the galaxy. Then we discovered that our galaxy was one among billions in the observable universe. Each step has made us smaller, less central, less unique. The multiverse continues this trend to its ultimate conclusion. Not only is our galaxy not unique, not only is our universe not unique, but even the laws of physics we take for granted may not be unique. Everything we know could be just one version among infinitely many. This can be both humbling and disorienting. If there are infinite universes, then ours is no longer special. The things we cherish, the stories we tell, the meanings we find may exist in other versions, repeated endlessly. But at the same time, this repetition can be comforting. If there are infinite versions of us, then in some universes every possible choice we could make has been made. Every path has been taken, every future has been lived. Nothing is lost because somewhere, in some universe, it exists. Infinity in the multiverse means that possibility itself is never exhausted. Of course, the multiverse is not universally accepted. Some scientists argue that it is untestable, that we can never observe these other universes directly, and therefore it lies outside the realm of science. Others counter that indirect evidence through mathematics or cosmological observations may eventually provide support. The debate continues, unresolved. But even as speculation, the multiverse pushes us to confront the limits of our imagination. There is also the question of meaning. If there are infinite universes, does that make ours less significant? Or does it make it more miraculous that we find ourselves in one where life exists? Some argue that the multiverse explains why the constants of physics are tuned so precisely for life. If there are countless universes, each with different laws, then it is inevitable that some will support life. We exist in one of those simply because we could not exist in the others. The multiverse becomes an answer to the puzzle of fine-tuning. But others argue that this explanation feels hollow, that it shifts the question without resolving it. Why should there be a multiverse at all? Emotionally, the idea of infinite universes can be overwhelming. It stretches beyond the comfort of boundaries, beyond the security of one cosmos. It suggests that reality is larger, stranger, and more fragmented than we ever imagined. But it also echoes something ancient, the sense that the universe cannot be contained, that beyond every horizon lies more. The multiverse is not just a scientific hypothesis, it is the latest form of a timeless human intuition that existence is bigger than it seems. And so, when we speak of parallel universes and the infinite multiverse, we're not only discussing equations or models, we're touching on one of the deepest questions we can ask. Is this universe all there is? Or is it one among endlessly many, a single drop in an infinite ocean of worlds? The answer, if it ever comes, may reshape not only science but our entire sense of existence. Infinity is not just a mathematical concept, not just a question for physics or philosophy. It is also an emotional experience. When people think about infinity, they rarely do so with neutrality. The thought can bring comfort, or it can bring unease. Sometimes it even does both at the same time. The idea that something has no end reaches into us in a way that other scientific concepts do not. It touches our sense of scale, our place in the universe, our hopes, and our fears. Part of the comfort comes from the promise that infinity seems to hold. If something is infinite, then nothing is ever truly lost. If time is infinite, then there is always more to come. If space is infinite, then somewhere out there, every possibility exists. This can be reassuring when faced with the finitude of our own lives. Against the certainty of mortality, infinity whispers of continuity. The universe goes on, even when we do not. Our brief existence becomes part of something without end. Religions and philosophies have long drawn on this comfort. Many traditions describe eternity as a kind of infinity, whether it is eternal life, eternal cycles of rebirth, or an eternal presence that sustains existence. The idea of infinity becomes a promise that there is more beyond what we can see, that the end is not the end. Even without religion, some find solace in the thought that time itself stretches forward without limit, that the story of existence never truly concludes. There is also a sense of beauty in infinity. To stand under the night sky and feel the endlessness of stars can bring awe, a sense of connection to something greater. Infinity can inspire, making our own concerns feel smaller and lighter. If the universe is infinite, then our problems, however overwhelming in the moment, shrink in comparison. Infinity gives perspective, a reminder that we are part of something vast, mysterious, and enduring. But the very things that comfort us in infinity can also unsettle us. The thought of endlessness can feel overwhelming, almost suffocating. If time never ends, then what does that mean for existence? If everything possible happens, then does anything matter? Infinity raises the fear that meaning is diluted, that in the endless expanse of possibilities nothing is unique, nothing is lasting. Comfort turns to unease when infinity suggests that our choices are small ripples in an ocean too vast to notice. Another source of fear is the human inability to fully imagine infinity. Our minds are built to handle the finite. We understand beginnings and endings, limits and boundaries. When confronted with something that refuses those categories, the mind strains. Try imagining eternity. Try picturing endless space. Sooner or later, thought falters. Infinity becomes a void, a place where the imagination cannot land. That void can feel terrifying, like standing at the edge of a cliff that has no bottom. There is also the fear of insignificance. If the universe is infinite, then what are we? One planet among countless planets, one life among countless lives, one story among infinite stories. Infinity can make us feel small, disposable, lost in a scale too large to matter. For some, this is unbearable. The thought that nothing we do could ever register against infinity can lead to despair. Comfort turns to dread in the same concept. This duality is not new. Ancient thinkers wrestled with it just as we do. To the Stoics, infinity of time meant that everything repeats, that the universe cycles eternally. For some, this was comforting. For others, it was oppressive, a reminder that novelty and uniqueness were illusions. To Christian theologians, infinity was a property of God, a source of comfort in divine eternity, but also a source of fear in the idea of eternal punishment. Infinity has always carried both promise and threat. Psychology sheds light on why infinity evokes such strong emotions. The human brain is wired to seek patterns, to impose order, to understand through boundaries. Infinity defies this wiring. It resists being contained in thought. When faced with it, the brain alternates between awe and anxiety, between wonder at the vastness and discomfort at the lack of control. Infinity presses on the limits of cognition, exposing the edges of what we can handle. At the same time, infinity speaks directly to our deepest desires. We long for permanence, for continuity, for something that outlasts us. Infinity offers that. But we also long for meaning, for uniqueness, for a sense that our lives matter in the grand scheme. Infinity threatens that. It promises everything, and, in doing so, risks making everything meaningless. Comfort and fear are bound together in the same thought. Even in science, this duality is felt. When cosmologists describe an infinite universe, some are excited, imagining endless discovery, endless variation. Others hesitate, wary of the philosophical implications. If every arrangement of matter exists somewhere, then science itself risks losing its explanatory power. If everything happens, then nothing is surprising. Infinity here again is both a source of wonder and a source of unease. For ordinary people, the experience of infinity often comes in quiet moments. Looking at the stars, or contemplating the endless stretch of the ocean, or lying awake at night thinking about death. In those moments, infinity feels close, not as a concept but as a sensation. It can bring peace, the sense of being part of something larger, or it can bring anxiety, the sense of being lost in something too large. Both reactions are deeply human. Both are part of what makes infinity such a powerful idea. In the end, infinity comforts and frightens us because it mirrors our own lives. We are finite beings who long for the infinite. We seek permanence in a world of change. We crave meaning in a universe that may not provide it. Infinity reflects those desires back at us, offering both reassurance and challenge. It tells us that existence is larger than we can ever know, but it also asks us to live with that knowledge. The comfort and the fear are inseparable. When people first hear the question of whether the universe is finite or infinite, it sounds like something far removed from ordinary life. It seems like the kind of puzzle that belongs in textbooks or observatories, not in daily experience. After all, what difference does it make to someone waking up in the morning, going to work, sharing a meal, or falling asleep at night? But the more closely you look, the more this question reaches into every part of how we see ourselves, how we think about meaning, and how we live. The size of the universe may not change whether the sun rises tomorrow, but it changes the framework in which we understand what that sunrise means. If the universe is finite, then it is a whole, complete in itself. It has boundaries in some sense, even if they are not edges you can touch. It contains everything, but only once. The stars you see are unique. The galaxies are unique. Even your life, fleeting as it may seem, is unique. There will never be another exactly like it. Finitude makes existence precious. Every moment is a singular event. Every pattern happens once and is gone. In a finite universe, the rarity of things gives them meaning. On the other hand, if the universe is infinite, then nothing is singular. Every arrangement of matter must occur not just once, but infinitely many times. Somewhere there is another Earth. Somewhere there is another you. Somewhere there are endless variations on every decision you have ever made. In such a universe, the meaning of uniqueness dissolves. What matters is not rarity, but abundance. Every story is told endlessly. Every possibility is realized. Infinity makes existence expansive. It stretches meaning until it is not about singularity, but about participation in the vast flow of all possibilities. Which perspective feels more comforting depends on the person. For some, the idea of uniqueness is essential. A finite universe offers reassurance that our lives are singular, irreplaceable, and meaningful in their one-time occurrence. For others, infinity offers comfort because it suggests that nothing is lost. Every path is taken somewhere. Every choice exists somewhere. Even if this version of us is finite, other versions continue forever. Infinity promises continuity when finitude threatens loss. But beyond comfort, the question shapes how science itself proceeds. If the universe is finite, then in principle it can be fully described. Its volume, its matter, its history could be measured, at least theoretically. Science could aspire to a complete picture, a total account of existence. If the universe is infinite, then no complete description is possible. There will always be more beyond what can be observed, more beyond what can be measured. Science in that case becomes an endless journey, never a finished map. Whether the universe is finite or infinite changes the very scope of scientific knowledge. It also changes how we think about origins. In a finite universe, the Big Bang is the beginning of all that exists. There is nothing beyond it, nothing outside it. In an infinite universe, the Big Bang may be only one part of a larger structure, one bubble in a froth of countless others. Origins shift from absolute to relative, from the birth of everything to the birth of our part of everything. Infinity turns beginnings into continuations, endings into transformations. Even ethics and philosophy feel the influence of this question. In a finite universe, choices carry the weight of uniqueness. There is only one version of this decision, this action, this life. That makes responsibility heavier, more immediate. In an infinite universe, choices still matter, but they matter differently. Each decision is one among infinite variations, one thread in an endless tapestry. Some find this freeing, the thought that mistakes are not final because other versions exist elsewhere. Others find it undermining, the thought that their actions are diluted across infinite repetition. Infinity complicates how we measure meaning in action. There is also the question of scale. In a finite universe, the sheer immensity is already beyond comprehension. Even if bounded, it stretches across billions of light years. For all practical purposes, it may as well be infinite to us. In an infinite universe, the immensity becomes literal. There is no end, no boundary, no limit to scale. This amplifies both awe and insignificance. Against infinity, our place feels smaller than ever. Against finitude, our place feels precious in its rarity. The human response to these possibilities reflects deep psychological needs. Some need boundaries to feel secure, Others need openness to feel free. Some are comforted by the thought that everything is contained. Others are comforted by the thought that nothing is ever contained. Whether the universe is finite or infinite matters not only to science but to the heart, because it forces us to face what we want from existence itself. And yet, in another sense, perhaps it does not matter. Whether finite or infinite, the universe is vast beyond comprehension. Whether bounded or unbounded, our daily lives unfold in the same rhythm. The sun still rises, the earth still turns. We still live within the narrow scale of human experience. The stars above are out of reach, whether there are finitely many of them or infinitely many. The practical difference is small. The emotional difference is enormous. This is why the question endures. It is not only about physics, it is about perspective. It is about how we locate ourselves in the cosmos. It is about whether we prefer a universe that is rare and singular, or a universe that is abundant and repeating. It is about whether meaning comes from uniqueness or from participation. It is about how we live with limits and how we live without them. So yes, it matters whether the universe is finite or infinite, not because it changes the laws of motion or the flow of time in our daily lives, but because it changes how we think about those laws, how we think about ourselves, and how we think about existence itself. The answer, whatever it is, will not change the fact that we live finite lives, but it will shape the story we tell about those lives. And in that way, the size of the universe matters as much as anything can. As the long journey of thought winds back to stillness, the question of whether the universe is finite or infinite lingers not as something to solve once and for all, but as something to live alongside. Infinity is not a puzzle with a final answer. It is a presence, always nearby, shaping the way we see the sky, the way we measure time, the way we think about ourselves. Whether we are speaking of galaxies without number, or moments without end, or patterns within patterns, infinity has become a companion to human thought, a shadow and a light, sometimes overwhelming, sometimes comforting, always returning when we ask what it means for anything to exist. Infinity is in the stars above us, in their number and in their distance, in the way their light travels for billions of years and still reaches us here on Earth. It is in the space between those stars, vast and dark, stretching farther than our eyes or our instruments can follow. It is in the thought that beyond every horizon lies another horizon, that beyond every answer lies another question. We cannot look up at the night sky without feeling, in some quiet way, the brush of infinity. It is also in the time that carries us forward. Each moment gives way to another, and no matter how much has already passed, there is always another waiting. Even if time began with the Big Bang, it stretches forward with no clear end, a ribbon that may outlast all stars and galaxies. The future, unlike the past, never feels closed. It always feels open, promising more. That openness is infinity woven into our daily lives, a quiet companion every time we look ahead, every time we wonder what comes next. Infinity is in the smallest things as well. In the branching of a tree, in the veins of a leaf, in the jagged line of a coastline, in the swirl of a seashell. Fractals remind us that endlessness can live inside limits, that infinity does not always require distance or time, but can reside in detail, in patterns that repeat without exhaustion. Holding a piece of Romanesco broccoli in your hand, with its spirals upon spirals, is enough to glimpse infinity at work in the ordinary, to see how the infinite can hide inside the finite. It is in our mathematics, the language we invented to make sense of the world. Infinity sits on the number line, not as an end, but as the refusal of an end. It lives in calculus, in the division of things into endlessly smaller parts, in the summation of endlessly larger totals. It lives in Cantor's discovery that infinities come in sizes, that there is no single infinity but an endless tower of them, each larger than the last. To study numbers is to live with infinity always in the background, always shaping what can and cannot be counted. It is in our imagination too. The thought of parallel universes, of other versions of ourselves, of infinite variations of every choice, may or may not be true, but it reminds us of the reach of our minds. We cannot help but wonder what lies beyond, what might exist beside us, what other worlds could be spinning silently out of reach. Infinity is part of wonder itself, the reason questions never run out, the reason the unknown remains vast no matter how much we learn. For some, infinity is frightening. It makes us feel small, lost in something too large to grasp. It suggests repetition, dilution, the loss of uniqueness. It shows us that our lives may be just one thread in an endless weave, one moment among countless moments. But for others, infinity is comforting. It means there is always more, always another chance, always another horizon. It means that our smallness is not the end of the story, but part of something larger. The same thought that frightens can also soothe, depending on how we hold it. Perhaps this is the truest role of infinity, not as an answer to be pinned down, but as a reminder of possibility. Infinity does not resolve our questions. It deepens them. It does not confine our imagination. It expands it. It does not give us certainty. It gives us wonder. To live with infinity is to live with openness, with a world that is never finished, with a cosmos that always holds more. And so, whether the universe is finite or infinite, whether time is bounded or endless, whether space loops back on itself or stretches forever, infinity remains our companion. It sits in our language, in our science, in our myths, in our mathematics, in our emotions. It is the quiet background against which all finitude plays out. It is the reminder that whatever we know, there is more to know, and that whatever we are part of something larger. Infinity is not only a property of the cosmos. It is part of how we encounter the cosmos. It is part of how we wonder. And in that sense, it is always with us, not as a conclusion but as a companion, walking beside us as we gaze at the stars, as we trace the patterns of time, as we drift into the quiet of the night. And with that, we'll let the questions linger a little longer. Infinity will not go anywhere. It will be here tomorrow and the day after, waiting whenever curiosity returns. For now, it can stay in the background, like a quiet star you know is there, even when you close your eyes. If you found these thoughts soothing, if they kept you company tonight, it would mean a lot if you liked this video or subscribe to the channel. It helps bring these calm explorations to others who might need them. Thank you for being here, for letting your mind wander gently through these ideas. Sleep well, rest deeply, and I'll see you again next time for another slow journey into science and wonder.